दुनिया के बाकी हिस्सों में जब इंसान अपने वजूद के लिए लड़ रहा था, तब भारतवर्ष में महान संस्कृति का निर्माण हो रहा था, जहां हर धर्म के लोग एक परिवार की तरह रहते थे। पर इस मंदिर को बाहरी आक्रमणकारियों की नजर लग गई। 16वीं सदी में पानीपत का युद्ध जीतकर दिल्ली के तख्त पर लहराया मुगल सल्तनत का परचम। उस समय कई शासक और सल्तनतें खुद को जिंदा रखने की कोशिश कर रहे थे। भारतवर्ष में अगले 100 सालों तक कोई और शासक मुगल सल्तनत को मात ना दे पाया। 17वीं सदी में मुगलों का सबसे ताकतवर, बेरहम और निर्दयी बादशाह औरंगजेब तख्त पर बैठा, जिसने अत्याचार की हदें पार कर दी। पर जब जब धरती पर आतंक और अत्याचार बढ़ता है, तब तब धरती को बचाने किसी महापुरुष का जन्म होता है। समय आ गया था। साक्षात माता भवानी और भगवान शिव का अंश मां जिजाऊ की कोख से शाहजी राजे भोसले परिवार में जन्म ले रहा था। इस धरती को औरंग के जुल्मों से बचाने जिन्होंने स्वराज की जोत लगाकर मराठा साम्राज्य की स्थापना की, वो थे भारत भूमि के महानायक छत्रपति शिवाजी महाराज। उनकी लड़ाई किसी भी धर्म के खिलाफ नहीं थी। उनका संघर्ष कट्टरता और उद्दंडता के विरुद्ध था। उनकी बढ़ती हुई शक्ति से चिंतित होकर औरंग ने कई बार स्वराज पर आक्रमण किए, पर हर बार मात खा गया। औरंगजेब और उसकी बेरहम सल्तनत को ललकारने वाला अगर इस धरती पर कोई था, तो वो दक्खन का शेर, वीर पराक्रमी छत्रपति शिवाजी महाराज।
बंगाल से शाइस्ता खान ने शाही नजराना भेजा है आलमगीर।
तिब्बत की जंग में मुगलों ने फतेह हासिल कर ली है जहां बना।
माशाअल्लाह, माशाअल्लाह।
आलमगीर का इकबाल बुलंद रहे। दक्कन से खबर आई है जहां बना, दक्खन का सिवा मराठों का छत्रपति इस दुनिया से रुखसत हो गया है।
सुभान अल्लाह, सुभान अल्लाह। सुनते ही हमें मुगल सल्तनत का परचम पूरे हिंदुस्तान के कोने कोने में ऊंचा लहराता नजर आ रहा है।
आमीन, आमीन, आमीन। शिवाजी गया, अब दक्कन की जमीन खुद ब खुद हमारी जमीन से जुड़ जाएगी।
जब उसे आगरा में कैद किया था, तब शहंशाह और मौत दोनों की नजरों से बच के भाग गया था,
और तब से अब तक हम दक्कन पर कब्जा नहीं कर पाए। आखिरकार आज जहां पनाह का एक लौता अधूरा ख्वाब मुकम्मल हुआ।
कान तरस गए, पर आज भी कोई अच्छी खबर नसीब नहीं हुई। सिवा जैसा दुश्मन अब मिलेगा कहां? या अल्लाह, तुझसे नाराजगी उम्र पर रहेगी। जन्नत के दरवाजे खुले रखना। शेर आ रहा है। जश्न मनाओ। फकीरों को अमीर बनाओ। मराठा साम्राज्य के इंतकाल की खुशियां मनाओ।
next one, the difference of another thing. Welcome back. We are going to commence 10th session. This session is on laser additive manufacturing. I request Professor I.A. Palani from IIT Indore to come to the dais and chair this session. अच्छा पाल जी करेंगे यहाँ पे मेरे इसमें अच्छा ओके ओके सॉरी पालनी जी इसमें सेशन चेयर लिखा नहीं है अच्छा 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 दूसरा पढ़ रहा है सेशन 10 में पाल का तो भाई वो नहीं है सेशन पीपीटी ऑफ स्पीकर्स है अच्छा इसमें बायोडाटा में है
चेयर का अलग से है ना
एक मिनट ये रहा Oh, I'm sorry for the goof up. I request Dr. C.P. Pal to come to the dais and chair this session on laser additive manufacturing. Dr. Pal is a renowned expert on laser additive manufacturing, and he also heads the AIC Pi Hub Atal Incubation Center of Raja Ramanna Center for Advanced Technology, where he has been instrumental in transferring this LAM technology to various industries. His recognitions, accolades are listed here. Over to Professor Pal.
Thank you very much, Dr. Rajit, for introduction. So we have this session on laser additive manufacturing. And you know that the keynote address was also by Professor Aimanna, and then we were focusing on, he talked a lot about laser additive manufacturing. So in this session, we have 3 talks. First talk is by Professor I.A. Palani from IIT Indore, who had done really very good job. And then after that, we have Dr. Natarajan Satish from AMPRI, Bhopal, and then Dr. Ravi Bathe. So all the 3, all other, stalwart in the area of laser additive manufacturing, contributing heavily, making the things, taking the India to the front of laser additive manufacturing field. So I will not take much time. I'll invite Dr. I.A. Palani from IIT Indore to come forward for the presentation. So Dr. Palani has research interest in laser micro 3D printing, and then micro and nano manufacturing, laser-based surface processing. And he's a fellow of Indian Institute of Engineers, and he also won the accorded with the ISSS Young Scientist Award in 2021. And one of the things is that one of the machines that they developed at IIT Indore, especially on laser micro 3D printing, got the award in the IIT consortium when they organize the award. So this is really leading work they are doing in the field of IIT management.
In fact, we started with the first student. We had these facilities, and then we could establish this printing of shape memory alloys. And then slowly, I also started working on additive manufacturing, so we could work on this macro level. So I could establish a good wire arc-based additive manufacturing, focusing on shape memory alloy development. So this is one technology which we had developed at IIT Indore, which I would like to project it over here in this National Laser Symposium. Okay.
So Professor Palani, you have 25 minutes for the presentation, 5 minutes for the discussion.
Yeah, sure. So, like as far as additive manufacturing is concerned, so we all are aware about a macro level processing. So when we try to print a macro structures, like we have wide variety of technology in hand, like DED processes there, powder bed fusion processes there. However, the work which I am focusing is upon developing certain amount of micro devices. So the thought process behind this particular technology is something like, so there is a concept called laser decal transfer based technology. Okay, in fact, the motivation behind this particular process is, like most of you are aware about this microelectronic system, basically developing a sensors or micro actuators, in fact a kind of micro robotic systems, etc. Whenever we try to talk about microelectronic system, the first thing which comes into our mind is lithography process. So people used to say that lithography is required for establishing a micro, for developing a micro device, etc. So what we thought is, why don't we, like as far as this lithography is concerned, so it has a wide spectrum, but highly it is used for developing a features less than 1 micrometer. However, there is a window is there between 10 micron to 1 micrometer. So for printing such kind of structures, there is a kind of a vacuum where we can develop a kind of a 3D printing technology, so that we can develop certain amount of sensors in this particular domain. Now, one of the key aspect which is involved in this is, like if you see, like for example, if I am printing certain amount of features, so we may need to go for a kind of a, so we may need to go for a kind of a mask. So as far as this mask is concerned, so I can just show some features over here. If this is if these are the features, so in order to prepare these features, like I may need to prepare a mask, then I can go for a kind of an evaporation technique, and using an evaporation technique I can develop these features. Now the interesting part in this is, like I need to invest more amount of money and time in preparing this mask. So this was the thought process. What we thought is, so let us work in a window of close to around 20 micron to 2 micron, so that we can promote the concept of maskless manufacturing. So using this maskless manufacturing, so what happens is, so you don't need to worry about a mechanical micromachining or a certain amount of laser micromachining to prepare a mask. So we can directly go for printing the features, so that it gives you a flexibility of printing any kind of features. Second point is, like we have been talking about the feedstock. So feedstock is one of the restriction for printing certain amount of materials. For example, in the case of shape memory alloys have a potential application in different strategic areas like actuators, sensors, etc. But commercially, when you try to take a shape memory alloys, widely we get it either in the form of a powder form or in the form of a wire form, or sometimes we get it in a plate form. So this almost restrict us to use these, to use a specific technology for printing such kind of shape memory alloy structures. So in this regard, so what we thought is, why don't we develop a kind of a thin film based 3D printing technology, so that we have a flexibility to develop thin films using different techniques, like we have a PVD process, CVD process, which are available and which are well established also, so that we can use those technologies to develop a feedstock, and from using thin film as a feedstock, we can go for a continuous printing applications. Now, so for this we have chosen two different technology. So one is called as a laser decal transfer based technology. So basically, if I try to classify is, so there are two basic systems are there. One is called as non-laser decal transfer based technology. Another one is called as a laser decal transfer technology. So if you closely observe this mechanism behind this non-laser decal transfer and a decal transfer, let me just introduce you to the different components which are available. For example, if I want to print a kind of a feature on a particular substrate, that I call it as an acceptor substrate, and the material which I am planning to print, we call it as a donor material, and this donor material is made to coat on a donor substrate using a thin film technology. So what we try to do is, when a laser beam is made to pass through this donor substrate, so we select the donor in such a way that this laser beam is transparent enough, it heats the donor material and it creates a micro droplet. This micro droplet will eject out of these donor material, and it will start depositing on the acceptor material. Finally, when we try to manipulate this acceptor substrate, we can create the features. Now, the interesting part in this is, like there is going to be a phase change of the material. Like ideally, when the material, when it is in the solid form, you are trying to convert it into a kind of a, like kind of a liquid phase or in a gaseous phase, and you are trying to collect those materials, the ejected materials, on the acceptor substrate. So this is one way we can use this technology for printing the features. The other way is something like, so we can use a laser decal transfer technology. So in this laser decal transfer technology, what we can do is, in between we will have a buffer layer. So when a laser beam is made to pass through a substrate, this buffer layer will completely absorb the laser beam, there will be a high pressure gas which will be created. This high pressure gas will be helpful for us for a pixel ejection or for the transfer of particle from one form, for the transfer of particle from the donor region to the acceptor region. Now, when we try to manipulate it, the donor region as well as an acceptor region, we can go for pixel by pixel printing, so that we can take care of the feature size and then we can print any kind of features what we are looking for. So the only challenge which is available over here is, like, I need to have a control over the ejection mechanism. I also need to have a control over the manipulation of this donor region as well as the acceptor region, so that I can print any kind of structures. Now, like when I try to talk about an application of this, like for example, so you have a capability in printing a certain amount of features on a silicon wafer, and if you want to print the same features on a flexible substrate, using this technology, this is possible. So only thing you may need to do is, whatever which is being printed on a silicon wafer, that can be efficiently transferred on the PET sheet or a flexible substrate, so that which can open a new domain with reference to flexible wearables or flexible electronics, etc. So this was the thought process. So what we did is, so we did our experiments. So initially we started with laser. So initially we started with a non-decal transfer based system. So in this non-decal transfer based system, so we used a 1064 Nd:YAG laser, and then in order to manipulate our beam, so in order to have a control over a beam, so we had a small aperture slit, and then we tried to have a simple XYZ stage with a donor substrate and a receiving substrate, and the transfer was well taken. So in fact, this was a kind of a preliminary experiment which we did to understand how this laser, non-laser decal transfer has a mechanism. So if you closely observe in this, so these are some of the investigations which we could observe, like for example, ejection analysis with reference for a defocus beam, so appropriately we can have a control over the ejection what we are looking for. But in this particular process, when we try to look into it, so this is a kind of a single spot which is getting generated. When we try to go for a spot with overlap, we could generate a kind of a splashy layer which is coming out of it, and then we try to go for a line pattern. Now, one of the major challenge in this particular non-decal transfer process is, like here, since the material is getting translated in the form of a kind of a vapor medium or in the form of a expulsed medium, so what happens is, like, it is very difficult to control the feature size what we are looking for. So this was one of the key challenge what we could observe with reference to a non-decal transfer, where exactly we were trying to look into the process. So what we did is, so we started moving into this technology of decal transfer based system. So for this decal transfer based system, so we took two different challenges. So like there is a kind of a challenge which exhibits related to printing a ceramic. So what we did is, we took two different ceramic. One is a kind of a zinc oxide, another one is silicon carbide. So those two materials we took as our kind of an experimental material, and we were trying to develop a features for it for a certain functional application. So as far as zinc oxide is concerned, so one of the key aspect is, so we all know about the growth of a zinc oxide in the form of a Wurtzite structure. So what we thought is, so if we can position the zinc oxide in a particular point, and then this, like positioning the zinc oxide will be helpful for us in the kind of like positioning the seed layer. By positioning the seed layer appropriately, we can have a control over the growth. Like for example, most of you who are working on this zinc oxide based optoelectronic applications, you might have heard about this whispering galaxy mode. So in order to create a whispering galaxy mode, it is required that we may need to position the seed layer appropriately, and we need to have a kind of a confined growth so that you can get a single crystal, and through the single crystal you can have a kind of a lasing medium. So what we thought is, for that application we tried to develop our technology. So first thing what we did is, so we used a sputtering. So using a sputtering, so we went for deposition of our zinc oxide. So before going into this deposition, so we went for a kind of a PDMS layer spin coating. So this PDMS layer spin coating will act as a buffer layer which can absorb the complete laser, and on top of it we went for a zinc oxide deposition, and this is a kind of a donor preparation what we had made. So this is a kind of a feedstock preparation what we had made for our micro 3D printing capability. And then okay, so these are some of the initial investigations what we did to confirm the overall uniformity of the film through this sputtering process. So using a non-contact surface profilometry, we could see a proper growth of the proper deposition of the film on the PDMS layer. Then, so this is a kind of a growth process which was evolved, and this is the experimental setup what we had developed. So I acknowledge Srinivasan sir who is over here. So basically we got a good amount of funding from DST AMT for this particular technology. So since we had showed our proof of concept, so with reference to that, so they gave funding to establish this technology, to develop this technology in the form of a machine. So what we did is, so the thought process is, so we have a donor region and an acceptor region. So we need to create a CAD model through it. Through a CAD model, so the appropriate G&M codes can be generated, and it can have a control over the donor substrate and an acceptor substrate appropriately to get a pixel by pixel formation. Now in this particular process what we did is, so we had a kind of a glove box. So in this glove box there is a beam bender, and then there is a focusing optics which is available over here. So this has a capability to control the overall focal point, and by this what happens is, we have a donor substrate over here. There is a place to keep the donor substrate, and then there is a position to have an acceptor substrate. This acceptor substrate region also had a facility to heat. That is, when there is a deposition which is happening, so what we thought is we can induce a strain with a heating, so that it improves the adhesion of the deposition. So with this, so we could develop this system, and then the overall heating capability, substrate heating capability was in the range of 25 to 300 degrees Celsius, and overall we had a lateral resolution of around 10 micrometer. So we used a carbon dioxide laser. So the reason for having a carbon dioxide laser is, since we are working on microelectronics, carbon dioxide lasers are transparent to silicon wafer. So whatever donor region we are creating on a silicon wafer, so that it can pass through the silicon wafer and it can be efficiently enough for transferring the material. So what we are looking for. Now this is the system which is established. In fact, there is a small animation which shows how the transfer happens. So the sacrificial layer what we have used is a PDMS which absorbs the laser beam, and then because of the expansion of the gas, the donor material will try to move forward and it sticks on to the acceptor substrate. So here the acceptor substrate what we have used is a kind of a small PMMA, or sometimes we have used a polyamide sheet, so that it is flexible enough to get attracted towards the particle which is sticking onto the surface, and with that we can print the structure. So this is a kind of a video which basically shows like how the structure is getting formed. Here you can easily see, so we have position at a particular point, and there is a kind of a pillar arrangement which exhibits over here, and this is a kind of a mechanism which is used for the ejected pixel. Now if we try to optimize the parameter, or if you try to look into the overall physics behind it, so like this is our buffer layer. Basically this is the kind of a sacrificial layer. So when the laser interact with the sacrificial layer, this sacrificial layer will absorb the complete laser, and finally it will result in a plume formation and expansion with varying time. So in fact this image we took through a high-speed camera to observe how the transformation happens. Now one important point which you need to see over here is, when there is a plume expansion is there, appropriately the velocity of the particle will also get increased. So this velocity of the particle will play a vital role when we try to print for pixel by pixel region. So whenever we are trying to optimize the parameter, we may need to efficiently have a control over this particular focal point as well as the energy, so that appropriately we can have the control over the velocity in which the particle moves and it sticks onto the surface. Now this is a kind of a complete study which we did with reference to the laser fluence as well as with reference to the velocity. In fact, it's a kind of a time resolved imaging along with the velocity measurement, so that like we can see how the tracks are printed with reference to different velocity. In fact, we can have a control over the track which is being printed, and overall also we can also have a control over the overall splashing which exhibits over here. So this is one important data which help us to optimize our parameter based on our requirement. Second important point is with reference to the zinc oxide ejection optimization. So in this regard, what we did is, we went for a kind of a different focal point. So this is a kind of a focal point in which first we tried with 9.8 centimeter, exactly at the focal point how does the feature behaves, and at 13.2 centimeter how does it behaves. So at 13.2 centimeter we can have a wider spot, and at 9.8 centimeter there is certain amount of distortion was observed, and exactly at focus, so we could get a clear kind of transfer which is observed over here. Similarly, we also tried to investigate the influence of laser fluence. So what we did is, so we took 3 different types of laser fluence. So one is with 15 joule per centimeter square, 40 joule per centimeter square, and 75 joule per centimeter square. And we were trying to optimize this transfer, pixel transfer, in such a way that there is no ejections are observed. That is, when you try to observe the ejection, at the outer boundary, there should not be any kind of extra material which is getting ejected. So we should focus only on the full width half maximum of the beam, and then the amount of material which is ejected exactly at the full width half maximum was observed, and appropriately it is being used. So then we also try to study the influence of spot overlap, which is considered to be one of the key parameter when we try to look into the device perspective point of view. Like whenever we are talking about a microelectronics application, interconnects plays a vital role. So when I am trying to print a kind of an interdigitated structure for a microelectronic application, so it is expected that the continuity of the complete printed structure should be there. So we try to investigate it. So what we did is, so we went for a different process parameter with reference to spot overlap. So we took 90%, 80%, 70%, and 65%, and we could observe how much is the kind of a splashing which exhibits, and how much is the kind of a proper interconnect which exhibits over here. In fact, I would say that like here almost like close to around 65%, we could observe that there was a proper interconnect which was established, and there was a less amount of heat affected zone which was trying to get generated out of it. Of course, by optimizing the focal point, so appropriately we can have a control over the interconnects. Now, like this is what I was mentioning, like we want to have a kind of a selective deposition of selective printing of these seed layers of zinc oxide. So this is a kind of a zinc oxide which was grown. In fact, we have used this technology called NAPLD. Using an NAPLD, we can grow a kind of a highly oriented structure on a silicon wafer, or in the form of a in the kind of a quartz also. So we used that, and then from that we were that was used as a donor substrate, and from that we were transferring it to a kind of a flexible polyamide, so that we can print the selective region what we are looking for. Now, like one of the key key point which I was emphasizing on this particular technology is, this material which is getting transferred, there is no phase transformation which is happening. So to ensure that, so we have done a kind of a XRD analysis as well as an FTR analysis to see, like we have done at the donor region and as well as an acceptor region, to see whether there is any variation is there, and there was no variation was observed. In fact, whatever functionality what we were looking for was pretty evident from the XRD as well as from the FTR analysis. So further, these seed layers has been used for a kind of a efficient growth process. Now, the second process what I would like to explain, second material which I would like to explain, is a kind of a silicon carbide material. So we all know about the overall property of a silicon carbide. Silicon carbide is widely used for kind of high temperature electronics application. One of the major limitations of silicon carbide is, silicon carbide can be efficiently grown using a CVD process. Okay. Whereas, like if I want to go for a kind of a pattern structure, so the mask based system only is deployed. So when you try to put a mask in a CVD process, it is very difficult for you to create a kind of a pattern structure. So what we thought is, like this is a kind of a work which we have performed for ISRO, basically for developing certain amount of piezoresistive sensors. So what we did is, so we took a silicon carbide, we went for a kind of an this RF sputtering. So using an RF sputtering, we could deposit a silicon carbide on a buffer layer. So basically the buffer layer what we used was a kind of a PDMS, and over this PDMS, so we have deposited the silicon carbide material. So we went for a thorough investigation with reference to thickness, because with reference to the thickness, already we have optimized our parameter for the efficient transfer. And now, so this is a kind of a parametric optimization what we did. So the thought process is something like this. We need to develop a kind of a H-based system, so H-based resistive system for piezoresistive applications. So some of the key points which I may need to look into it, we may need to look into it is, like we need to have a kind of a continuous interconnects over here. So for that, so first parameter what we are trying to optimize was the standoff distance. So with reference to standoff distance, so initially we started with 8.5 centimeter, where almost it's a kind of no material transfer was observed. There was a poor interconnect which was observed. Now with 10.5 centimeter, so what we could see is there was a kind of a uniform material transfer was observed. And then at 11.5, again there was a kind of a non-uniformity was observed. So we took 10.5 as our kind of a benchmark value, and through this benchmark value, we proceeded further for a kind of like with reference to varying power, because one of our main requirement is we need to print close to around 2 micron layer, close to around 20 micron layer was our requirement. So 20 micron layer, thick layer, which we may need to print over here. So for that, we took power as our requirement. So with reference to different power and with reference to different standoff distance, we tried a different value, like we went for power ranging from 3.5 to 5.5 watt, and okay. So with reference to 3.5 and 5.5 watt, so we changed the different parameters, and where we could observe at 4 and 4.3 watt, we could get an efficient transfer with the same 10.5 centimeter standoff distance. Now, we also studied the influence of spot overlap. So already we had observed this in this particular technology. When the spot overlap is in the range of 60 to 70% overlap, you get an efficient transfer, which is once again which is proved over here. And this was a kind of a technique which we had followed. So what we did is, for one track, we could go up to 2 micron thickness. So when you want to go for a 20 micron track, so we may need to increase the number of layers. So we increased the number of layers, and we were continuously studying the overall thickness configuration. So like we went for, initially we went for 3 layers, then slowly we had a kind of substrate heating capability, and we went for 5 layers, where we could print close to around 22 microns. So what we did is, so by adjusting the standoff distance, so we can have a good throughput, and then we could build the layer. And we also confirmed the characterization, like before printing and after printing, is there any kind of external phases are available over here. And this is a kind of a thickness which we could get around close to around 12 micron, 20 micron and 26 micron layers of silicon carbide, which we could print over here. And this is the final structure which we had printed and we have given to ISRO. So close to around 12 samples we have given to ISRO for, it was against an order. So and now currently the characterization is going on for a piezoresistive structure. Okay. So in summary, as far as this particular technology is concerned, this technology is a kind of a unique technology of its kind, where first time we are using thin film as a feedstock, and we are trying to develop a kind of a maskless manufacturing, basically in a particular domain ranging from 2 micron to 20 micron or 30 micron, wherever you don't need to invest on the mask. Since you are working on a thin film, since you are using feedstock as a thin film, so you have a flexibility to print any kind of layer. So that is one advantage which we had proved. So further more to go. So we are also working on integrating one more femtosecond laser for developing a micro additive as well as a micro subtractive system in it. So in fact, these are some of the devices which we had printed. So recently we have also printed some strain gauges, and we have delivered to ISRO and DRDO for further testing. So it has a capability to print a certain amount of hexagonal interconnects as well as interdigitated structures using this structure. Okay. So I would like to thank my laboratory. So so I have a good group, a good amount of students who listen to me and who are self-motivated. Close around 2 people have worked on this. One is Dr. Anshu. So in fact, I should thank Dr. C.P. Paul to give Dr. Anshu from his lab to my lab to work in this particular product. And then we had Mr. Arpit Singh, who is continuing on the functional development. And there is quite a good amount of master students and undergraduate students who are closely working this particular part. And we would like to thank our funding agency for developing this particular product. In fact, I should thank DST. So continuously we are getting close around 2.5 crore to establish this particular technology, and some more are in the pipeline from DRDO and ISRO. And thank you very much for the opportunity.
Thank you, Dr. Palani. Now session is open for the QA session. Any questions?
Yeah. Yeah, please, I think you can speak.
When I look at the 3D printing of the plastic, it always be a single color. It's look like boring, like blue or yellow or something like that. So the reason is that we can infuse 3 to 4 filaments. So I have a doubt that in this kind of 3D printing, laser additive manufacturing,
micro 3D printing,
can we do the same thing, like we can infuse different material with thing?
Yeah.
Like your idea is go to with a substrate mask and they are depositing it. So that's thing. And what about the plastic case? So is it possible that we can infuse multiple of colors of 3D printing like that? When I creating a product, it looks great, not rather than boring one color thing.
Okay.
Are you getting my point?
Yeah, I am getting your point. So actually, if I try to quantify it, let me just quantify it with reference to a micro level and a macro level. Okay. So in the case of a micro level, so here, like you might have seen, so I am printing layer by layer, and I have a donor region. From the donor region, I am printing it. Suppose I want to print 2 micron of nickel, 2 micron of titanium, 2 micron of nickel, 2 micron of titanium, which is possible. So only thing is, so I need to keep one donor layer of nickel, one donor layer of titanium. I need to bring this for printing one layer, then I need to take it off and put there. So like that we can print a kind of a sandwich layer, what we are looking for. This is on a micron level with this. Now to answer to your second question on a macro level, there are many 3D printers are available with multi-nozzle system. Okay, so where if I want to have a red and a yellow, it is possible. Okay, so 3 to 4 nozzles, it is easily available. Of course, there are some possibilities to have a customized system also. I think
yeah, it's possible.
Yeah, right,
it's possible, and multi-material is available, multi-color, multi-filament also. Now, if you talk of the FDM, there are now many PLA is there, then ABS is there. So even the multi-filament is possible and is doable. And the models now, they are able to select the parameters which are required to be printed, and it's done. So not only the color, but also the material is doable now.
Property also.
Yeah, property can be done.
It's possible.
Thank you, sir.
Yeah, Dr. Dahara here.
Yes.
I have a question is there any general understanding of shaping? Because see, you are doing now 3D, and from the keynote speaker, Professor Manna onwards, we are listening for complicated structure. But many times you need to sinter them or
post-processing.
So now post-processing, is there any general understanding how you can preserve the shape, size, everything after sintering? Because materials are changing. Mostly materials are changing. It's a material property. Like, is there any theoretical understanding how to really do it, or you just do it from your experience?
No, actually.
And if not, is there any requirement for such thing? Because now looks like that tomorrow we are going to the this 3D printing world. It is a different world now.
Yeah, actually, sir, as far as this to answer to this question, like in fact, I attended one conference. I think most of you might be aware about it. It is called as NAMRAC, North American Manufacturing Association. Last year when we attended that conference, that entire conference was related to modeling of additive manufacturing. So in fact, the main focus was something like this: to create a huge pool of data, kind of a multiphysics modeled data in such a way that you have a better understanding on the physics behind these particular processes. Okay. So when we try to look into the physics of this particular process, there are quite interesting aspects will come into picture. Like one of the main motto as far as technology perspective point of view, we are looking for a repeatability. So that is one of the key aspects which we look into it. So when we try to look into the repeatability, it is required to understand the physics behind. And currently I would say we have quite a huge amount of pool of data. With the pool of data, now we are marching towards in such a way that now today if you give a shape and if you give a material, automatically the data will be pooled and you get a kind of a finished product coming out of it. In fact, that is what we are moving towards, and many companies are also working upon, and we are ready for that. That is what I would say. Sir, you would like to add? Sir is the right person to say.
No. So what happens is, in this case, there are softwares available now. For example, you have altogether a new material available, and they have some standard pattern which are to be printed using your machine. The moment you do the printing, that particular standard patterns and do the measurement of that, maybe some optical method, other things, and feed this data into the software, and it will know what has to be corrected while making the shape. So that sort of things are available, and then you say this is now new material and these are the data we printed. It optimizes everything, and you have things available which prints the right way. So that level of the 3D printing we are today talking at the global level.
So we can directly get a final finished product.
Yeah. Dr. Upadhyay, this is the last question, right?
I think he's waiting for.
Thanks for the talk, sir. Sir, can you please go to the slide talking about decal transfer of deposition?
This one?
Yes, sir, yes, this one. So in the laser decal transfer method, you are basically using a pixel to structure.
Both. I am using pixel to pixel.
Yes, sir. So how, precisely, can you control the pixel size over here?
Okay. So the pixel size has a direct relevance towards your focal point.
Yeah, focus spot size.
Focal point and your spot overlap. Okay. So by optimizing your focal point and a spot overlap, we are trying to go for a pixel by pixel transfer. Now, if I understand correctly, your question is something like, when I am inputting a laser on the donor region, how you are getting translated in the acceptor region.
Yes.
Okay. See, this is where exactly this aperture plays a vital role. So we try to ensure that we are not using the complete beam profile. So we are just trying to cut off the flange, and we are using only the full width half maximum region alone. Okay. So when we try to use a full width half maximum region, so the high energy point alone will be involved and it will be absorbed, and then there will be a splashing of material which happens. So when we try to talk about the splashing of material, so the transfer will not be a proper circle. Okay. So in fact, there will be a kind of a spillover at the edge. So like for example, if I want to print close to around 2 micrometer, it will be close to around 2.1 or 2.2 micrometer along the size. But by going for a 60% overlap, we try to make an average out of it, so that we are within the tolerance limit. That is what is the thought process we are.
My motivation was can we make grating features of macron sized using this method?
Yes, actually the main motto is
I will suggest intervene. What can you do is you can plan a visit to his lab and see and discuss with the students. That probably will give more awareness about the stuff. And since you are from RRCAT and we have a very strong tie-up, anytime you can plan, we will arrange the visit also.
Yeah, you can take my number.
Yeah,
and
that would make the last question is from Dr. Upadhyay, please.
Upadhyay, sir, please.
Okay, I wanted just ask how you are, because it is a vaporization and then melting in between, I think you are working.
Yeah, actually yeah, you can complete your question, I can explain.
To vaporization and melting. Then when it is splashed onto the surface, how you control whether the beam size of the ejected material is 2 micron or it is going beyond that 20 micron. So beam size will also affect on that, or?
Yeah, the focal point size will have an impact on it. So what we have done is in the machine, so we have integrated a small microscope. So through the microscope, we get a feed on the pixel what we are printing it on it. Okay. So so of course currently what we are using is a carbon dioxide laser. So you know that carbon dioxide laser beam has some kind of variations. So that is why we have a kind of a bigger tolerance. like if we want to print 2 micron, so we get close around 2.2 or 2.3 micron. Okay. But we are trying to efficiently take care by going for a overlap, so that appropriately we average the process. So in fact, that is the thought process. We are trying to convert this carbon dioxide into a femtosecond laser, so that we can have a precise control over the printing. Thank you very much.
Thank you, Dr. Palani.
Thank you very much for this opportunity.
Dr. C.P. Paul to please present memento to Dr. Palani.
So next talk is from Dr. Natarajan Satish from CSR EMPRI. Dr. Satish is also one of our collaborators, and we had been working with him on the laser type manufacturing of graphene material with the metals. And he has done a really good job, and now over the period they have developed a very nice 3D printing lab now at CSR EMPRI. Not only the metals, but now they have e-beam, even the bioprinting facility they have established. So with this introduction, I hand over the stage to Dr. Satish. Over to Dr. Satish, please.
Thank you. Pointer. Okay. Good morning, respected Dr. C.P. Paul, and giving me opportunity to present here. And I see a good gathering here on the Saturday. So I will present some of the work here on the laser additive manufacturing of emerging materials. I have put it as emerging materials, and you will see what are these emerging materials and how we can actually leverage the process of actually additive manufacturing to this gap. Okay. So we actually as an EMPRI, we work on basically two aspects. One is the manufacturing processes as well as the advanced materials. Advanced materials is that, as you know, that advanced materials not only just functional materials. In structural materials also there are lots of advanced materials, construction materials also there. And in emerging materials, there are different kind of emerging materials also comes up. And manufacturing process, you know, all this traditional manufacturing, most of the things people has worked on this. Now the thing is that there is a shift coming up, that is basically mass customization, which is going to drive the economy, where actually, you know, several parts are comes up in that industry 4.0. One of that is basically your additive manufacturing and IoT and AI, you know, all these things comes into the picture of that. Okay. So how we are going to do what we are going to do in this direction is that, like as I said, EMPRI is Advanced Materials and Process Research Institute, where we have, you know, different kind of materials. You can say that from graphene based materials to different kind of characterization, metallurgy materials, and all these things are there. And we have also process technologies, where different kind of processing technologies are there. One of that area I am working on that, actually I am from physics background, I work with materials and engineering people and also the chemistry people. It is a interdisciplinary research area where we work as the graphene materials to the additive manufacturing process. How do we bring it into that? Okay, so these are the, like, you know, all emerging materials, new materials we can call, or advanced materials. You know, graphene or borophene, maxenes, and also you have different carbon based materials and conventional materials are there. You know, hydrogels also it is there. Then you have, how do we use it to make a composite or end use applications, right. So, one of the areas where we can think about is like aerospace, space, automobile. There are different applications. So, different applications requires different desired properties. Okay, this is how you are going to tune. Okay, why you wanted to make these materials? Because it always require, for example, aerospace, you need a low thermal, good thermal conductivity, low weight or high strength. Then you need in space, you need a low CT, thermal expansion coefficient has to be almost close to 0. Like this, different kind of parameters or properties are required. So, if you understand the requirement, then if you tailor made your materials to reach a given property, that will be interesting to study it, right. So, in CSR Ampere, we have established Center of Excellence for Graphene and its application, where we are working on different kind of additive manufacturing. One is the laser and AB metal additive manufacturing, where we are trying to cater the need of manufacturing of graphene materials for structural or macro applications. Then bio 3D printing, where you can use the biomaterials based components or sensors for the different kind of additive manufacturing, right. So, then we have functional materials, as you know that all this kind of different kind of functional materials are there. Then again you need to use different kind of 3D printing processes, because 3D printing process or additive manufacturing process is same like your all conventional manufacturing process. You choose the materials are chosen based on your end application, then manufacturing process also differs. So, the same way you need to think about what manufacturing process suits. Here instead of an additive manufacturing process are different combination of things are there based on materials. FDM goes for polymer thermoplastic materials, then you have hydrogel, different materials are there, rubber, different inkjet printings are there. Same way you have different wide range of 3D printing processes are there. So, we need to think about all this kind of thing when you are thinking about the manufacturing. You have to think the process, what end use you need, what property you need, what material you have to choose, then you have to choose the 3D printing process accordingly. Okay. So, I will now come to the first metal additive manufacturing facilities, what we are doing with this. So, we have like 2 machines recently started. One is electron beam, here use 3 kilowatt electron beam in a vacuum, and it is again powder bed fusion, it is from G additive. And we have a laser powder bed fusion, it is came from the 3D systems. So, what we are going to do also for metal additive manufacturing, any additive manufacturing workflow requires different kind of processes, like you need a good design for additive manufacturing software, DFAM. Then you need, if you are thinking of re-engineering some of the existing component, you need a reverse engineering workflow as well on that. Then you need a material sample preparations, characterizations, or to remove from the bed, or if you need, for example, laser, we need a iridium to remove it, and you need to have also like a density measurement. So, these all the supporting facilities you need to create also with the additive manufacturing process. So, I will come to the main topic of this thing, what we have done in that. In Ampere, we first demonstrated stainless steel with the graphene. So, several PhDs already completed on this one, like what we are going to do that, how we are doing it. So, we mix the metal powders, basically it is gentle coating, mechanical exfoliation based coating is used, so that you are able to these metal particles are there, you coat here the graphene onto the surface of it. Okay. Now, once you coated it, you are able to use it for the different application. Right now, we are going to do it for the 3D printing. So, we can study, because graphene you can study it only through the Raman spectroscopy. We have to study that whether your graphene stays as a graphene in all your throughout the process. Okay, as received graphene after milling inside the composite, how it is staying there, we have to study it. So, we use the additive manufacturing process to manufacture it. So, you can see that what effect we have seen in the microstructure of that is that basically graphene, there was no this strength translation from as in this one. But what we have observed here is that there is a grain refinement process, we have observed it. So, through this grain refinement process, we are able to linearly vary hardness, or you can improve the tensile strength or UTS. In this case, we are able to achieve 0.28% graphene addition from 500 MPa yield strength up to 850 MPa this thing yield strength we can, and up to 1.1 GPa UTS we are able to achieve on this process. So, basically you are able to get high strength steel with a very good ductility in austenitic steel itself. So, then we have shown that also in aluminum alloy, because aluminum basically mostly it is not much spherical powders you get, and against there also we are able to coat the graphene, and we have studied because here near net shape achieving itself is the one of the biggest problems. So, we try to study it after adding a graphene, how much is the porosity still left on that, and uniformity of the graphene inside the matrix we have studied through the Raman spectroscopy and all mapping of that, and you can see the 3-dimensional microstructure of a given sample, and we also try to study it in depth, like for example, we can always ask whether graphene stays as a graphene, or it is goes into the as a carbon, or it is forming any other carbide formations, metal carbide formations or other thing. So, we have shown it through the atom probe tomography, also XP synchros and several conditions, that we are able to show that graphene was staying as graphene. In aluminum alloy, because it does not have a common phase with the aluminum, so it tends to attract most of the silicon or other metals, it is forming aluminum silicide or some kind of this thing, which is forming interface with the aluminum alloys. So, with this actually we try to convert it into the technology format, and now we are pushing it for the larger scale applications to the aerospace applications or defense applications. So, right now we have to certain extents we are able to manufacture it on the full bed scale of this stainless steel graphene or aluminum alloy graphene. Several publications has been carried out on this one from 2010, and this is the comprehensive of this aluminum additive manufacturing. After this stainless steel graphene or this one, now we are moving towards also titanium alloy as well as the Inconel. So, what we have observed is that in these processes, it is like casting additive, one can say is that. So, one can improve full bed scale 3D printing with a good uniformity and this thing, also uniform composition or this thing, one can actually pitch it as a casting additive. Similarly, you will be able to achieve the near net shape properties in a full bed scale 3D printing process. So, in this direction we are moving towards. We are also now trying to use, for example, CM247LC is there. It is one of the toughest materials to the 3D printing. By adding graphene, whether you can do it in the stabilize the gamma prime phase of the CM247 alloys and all. So, this way we can actually make a pitch for use of this advanced materials or emerging materials for the additive manufacturing of that. So, in this way what also we can add with this way you are able to increase the number of materials which comes to the additive manufacturing. So, we are going to add a new dimension to the additive manufacturing. Basically, you are trying to make new materials and all this one. So, that will be helpful to adaptation of the 3D printing for at least not in directly going for 3D printed component, at least on demand spares can be made or inventory reductions can be made. Then you can think about accelerating make in India or other thing. So, this is the phase manner, because right now we are not even starting in this direction, on demand spares and also reduction in spare part inventory. That will be very good starting point for this additive manufacturing to take it up on this one. So some of the problems normally we also face in all additive manufacturing is that actually uniformity, microstructure repeatability from one machine to another machine. Also like component scale uniformity. Normally, you know, in casting process or forging process, in everywhere we have like, you know, how many throughput is there, like how much is the efficiency of the process. If you make 100 component, only 10 are getting this thing, or 30 is getting validated. These are in industrial scale process. When you are doing, how much where we are positioning ourselves, that will also decide the cost point of view. So we have to see that how we can improve that, and we can actually pitch in as a additive manufacturing to replace the casting process. Lots of casting components are done, where actually like forged components replacing with additive manufacturing is right now is not in domain. It's a little far off from right now, because right now we have to reach to the near net shape to this thing, but E-beam can do there, actually still there. But these are the things we have to address this one before we can reach to the commercial scale adaptation of that one. So for that also we have done some analysis, so that what we are trying to do is that we different length scale microstructure, how the microstructure gets affected on a large length scale. We have done it through the image analysis and network analysis of that one. So we are able to generate, for example, different length scale, different microstructures are there. For example, these are subgranular cellular networks are there. Then again on this you can very nicely map it. Then again in this is a generation of the graph. Then this is again on eBSD, how we are able to generate. eBSD basically your grain structure, right? So you can generate the grain structure network as well. Then again you go into the TEM images, you are able to get the dislocation network. So you will be able to see through the all the fundamental deciding network structures, and you are able to map it through the different length scale. So once we are able to do that, and we have seen that how it is going. So we can see that by adding a graphene, you are able to see that the change is happening only on TEM. That is basically adding a graphene is actually changing the number of dislocation which is being created. That is how, that's basically strain hardening effect. Basically what we have observed is that by adding a graphene in additive manufacturing, we are actually introducing basically strain hardening. It just increases the number of the dislocations on the length scale. Otherwise grain structure reinforcement and other things has not changed much in this one. So we are able to identify at which length scale we are able to. Now we are trying to integrate this process with the AI based melt pool monitoring, so that we will be able to get control of the full bed scale manufacturing and repeatability and reproducibility of that. For that now we are trying to come up with the reinforcement based algorithm, so that we will be able to get into the manufacturing of this one, additive manufacturing. With all any additives, any other materials, we will be able to push it through the commercial scale manufacturing of this ones. So then I will come little bit about the functional materials, like I will try to skip it through faster. So what we have shown is that through the additive manufacturing, we are able to make a graphene based ink, and you are able to 3D print it. These are very conventional piston and syringe based ink extrusion process, which is loaded into the your 3D printing. Okay. So you are able to make ink, graphene ink with no additives, just aqueous based ink, which you are able to 3D print it and demonstrate it in a flexible supercapacitor based applications, which was published in Carbon Letters. Then again Journal of Energy Storage, where actually you have electrode as a graphene, then electrolyte you can make it using the solid state for solid state energy, using a graphene quantum dot in a hydrogen. So this also published in Journal of Energy Storage. Again it is used in the same 3D printer. This one, Ultimaker 3D printer, Discover is basically a extrusion based system with a syringe mounted on this one. So So, you can directly 3D printer these functional materials into the devices directly. So, these are the structures of the 3D printer, this one, how it works and 3D printer structures. And you can even directly 3D printer intuitively using the graphene, also using the electrochemical 3D printing process. Again, we have developed in our Ampere. Then again, you can also have a custom filament extruder, and you make any customized materials to the 3D printing for catalysis applications and all. This area also we are actively working in CSR Ampere. Then last and not but least, this the bio 3D printing also we have very recently established, and we will be trying to complete this process and develop a graphene through graphene based materials for biomedical applications and also. So, I will give little bit of our one last this thing, Make in India Raman spectrometer, which was designed, developed and commercialized in CSR Ampere, which is at par with any international brand. You can take ASTM standards or NIST standards or CE certification or 21 CFR guidelines or any other thing, which was designed, developed and commercialized successfully from CSR Ampere. So, for now 10 purchase orders are received last 2-3 years, and recent and latest one is from PRL Ahmedabad. So, these are the purchase orders. Thank you.
Thank you, Dr. Satish. Now, session is open for QA.
Yes.
Just one query.
Yes.
Actually, this electron beam weld, electron method you are also going to add, electron additive manufacturing.
Yes, sir.
Electron beam based.
Yes.
So, how you think that it will be better or it will be comparative to laser additive manufacturing? How assess that?
Yes, sir. So, in electron beam, you have an advantage is that it is actually completely heated bed. That's around printing happens at around 1100 degrees. So, whatever the component you are going to get in those things is already sintered, or when you get near net shape, you will be able to get as good as your sintered or near net shape components and all. Right now, only constraint in electron additive manufacturing is that the surface finish, normally the porosity which you get on that, normally E-beam requires further VMC to finish the component. Normally, this is the constant of this one, and also the high capital cost right now. If you want to go any industrial scale E-beam machines right now, you wanted to purchase, it goes about 15 CR. What we have is about 6.5 CR, which is comparable to the laser machine. But these are this R&D based machines and all is there. And again, one more concern right now in E-beam is that it is not as open as a laser machine. Laser machine now you get like such a way that you put anything you wanted on your machine, but E-beam machines are not like that yet, because right now like G is making or Geol are making, they have few materials optimized it there. So, but it has a good potential. That is what we wanted to do here is that we open our machine, and if anybody is interested, they can come. We have fixed charges per hour basis. You bring your material and we put it and we can try it. So, that way we will be able to open lots of materials, because any additive manufacturing, for example, how do we replace the conventional manufacturing? You go to like stainless steel or this thing, thousands of alloy systems are there. How we are going to compete with that kind of versatility with few alloy systems in additive manufacturing? By bringing more and more materials. If we make our own materials, because materials technology decides any other technology, because most of the time if you see that all advanced technologies are restricted only through the materials technology, because they do not give what material it is, how it is made, how to process it. Once they restrict the materials technology, even they give you the machine, you will not be able to reproduce that. So if we develop our own materials technology, that is what we are pitching into that. We have to develop our own materials technology, our own materials, this thing. That is what we are embarking on that, because see, I am not going to replace some steel alloys which is there in Russia or this thing right now. But I can develop our own materials technology for additive manufacturing. At least somewhere we can start it as that. The same way we can do it for E-beam also. But it is right now limited by a very few number of materials are there.
I will add to the answer what Dr. Satish has said. The explicit advantages are threefold. Number one, we are working in the vacuum, so the purity of the material is one advantage. Second, if you talk of the deposition strategy, so what happened in E-beam, we'd go for the preheating of the material first, and then we go the deposition. So it is two-stage process. And the third advantage we have is in terms of the scanning speed. If we talk of our powder bed fusion, which is the faster than DED, then here we are talking of the speed in the range of 1 meter or 2 meter per second. But in terms of electron beam, we are working at the range of 25 to 30 meter per second. So that all changes the whole microstructure generation and other stuff comes into the picture. So these are the three distinct advantages to have a electron beam machine as compared to the laser based beam machine. That's what. So another question is there from there we can, yes.
Okay, namaste sir, thank you. So this question is also a random question that comes to my mind right now. I am framing this question like this, ki, this is my mobile phone.
Yeah.
Okay, and think about this is the laptop. Okay, so the fact is that if I am putting graphene layer, graphene thin film, so it becomes unbreakable. So now the point of view of a businessman is that we are not purchasing a new mobile phone because of the mechanical damage. So the future is going to be like that. The device won't go for a mechanical damage, and we are purchasing the iPhone 15 to iPhone 16. We got bored about it. Are you getting my question or not?
Yeah.
So the question is simple that today my phone, so मेरा mobile का screen खराब हो जाता है, टूट करके या कुछ पढ़ करके मेरा mobile का screen crack हो जाता है. But the fact is that in future, because of the graphene thin layer coat on my mobile phone upper layer, it won't break, for sure.
Yeah.
So it is very means you mentioned it gigapascal of energy so pressure you are putting, and it is not unbreakable kind of stuff. Yeah. So in future, the company are accepting this technology or became reliant to this technology. मतलब वो future में company वगैरह क्योंकि उनका sale तो mobile phone से ही होता है ना, mobile phone या computer बेच करके ही होगा. और जितना ज़्यादा बेचेंगे वो ही उनका profit होगा. मगर यहाँ पर mechanical damage future में होगा ही नहीं. Are you getting my question?
Yeah.
Okay.
So actually, right now, adaptation, you would have seen the graphene paints is there, which is coming up already. Graphene-based paint, you would have seen advertisement everywhere. But adaptation is there in everywhere in the industry, because industry or any manufacturer or any company, they don't wanted to see that their product is always there. They wanted to see optimize the value to the customer. Okay, this is where the business lies in. Okay, it's not that okay they wanted to sell you repeatedly, but they can sell it only when they give value to the customer. Otherwise, if they keep on going on this direction as you are saying, it is not, but it is being adapted. But as you said, it is not be completely unbreakable, because that will be the case when you make completely single crystalline graphene on the full surface. Right now, there is no technology available to make it on that large scale single crystalline graphene right now. If you are able to make it, that itself is a breakthrough technology. But what we use, or most of the commercial uses, that smaller graphene particles of 10 to 15 micron sizes, which is being used to enhance the existing material's properties. So in that case, what happens is that it gives you somewhere like a little bit enhanced properties, like the same way I have shown it. Graphene gets coated smaller micron particles of the stainless steel. So it improves the stainless steel property from 500 to 850 MPa strength, something similar like that. So you are going to give more value to the customer. Basically, more value for the material you are getting it. Okay.
My second question is that what is your technology for are you exfoliation is mechanical or electrochemical or means?
These are the commercial graphene what we use. It is basically thermal cum plasma exfoliated.
Thank you.
So let's start. You can discuss with him during the lunchtime. Thank you, Dr. Satish.
Thank you.
Maybe the lunchtime? Let me take the last talk, right?
So, as a matter of our token of our appreciation, we would like to present a memento to our esteemed speaker.
Thank you.
I invite the Paul to present the memento. Thank you, sir.
Actually, we started our session almost 15 minutes late. And I am sure the people who are asking the question, they were all missing out. So somebody has to sacrifice for it, right? So we are going to the third talk of the day, which is the last talk of the session, is from Dr. Ravi Bhathe from ARCI Hyderabad. Dr. Bhathe is from Dr. G. Padmanabhan's lab in you know that Padman Saab was one of the stalwart in the area of the laser processing. So a lot of work they have done, specifically in terms of the collaboration with Indo-US Science and Technology Research Forum. Then many stuff they have done, and they also have equally good facility available in terms of powder bed fusion, direct energy deposition, as well as the cold welding. So all these things they have. Over to Professor Professor Ravi Bhathe.
Okay. Thank you, Chairman, for a kind introduction of myself and my institute. So, good afternoon, all of you. So, today, actually, consult. So, I made instead of making a very specific topic, I make a more generic topic, and I want to highlight from transferring technology from lab to industry, what kind of challenges we are facing. So I plan my talk like this. First, I will give the introduction to the laser material processing, but I don't think in this gathering need this kind of introduction. I will go then some case studies we develop in our lab. So before going to my actual talk, I want to introduce my institute. Actually, most of people don't know what is a ARCI. ARCI is a Department of Science and Technology Autonomous Institute, and is working on development of material and process and transfer to industry. So far, we transfer 46 technology to the different companies, and about 250 application we develop the solution for industrial solution, and is working on different materials as well as the different processes. One of the center of excellence is laser material processing. So in this center for laser processing of material, so our mandate is promote and provide laser based technology to the technology for Indian industry. So we are having our center unique high power industrial lasers. So we are having a 10 kilowatt and 6 kilowatt direct diode laser. So those we are working in laser cladding and direct energy deposition. Then we are having a 400 watt and pulse NDAC laser. So mainly using for laser drilling application. Then CO2 laser. Also we are having state of art ultra fast laser, and also we are working in this laser additive manufacturing and electron beam melting process. So in this we focus on the area of laser surface engineering, then surface reclamation, laser based joining, laser micromachining, laser machining, and additive manufacturing. So I will not waste much time here. So I will also skip this side. So here, what I want to say here in the marketplace of the laser processing, if you see here, 1986 laser processing start in the market, and market is only 150 million US dollar. But now, if you see in 2023, market went up to more than what you call 22 million US dollar, and expected to grow very fast up to 50 million billion dollar in 2020 to 2034. So growth rate is, if you see, is more than 27% as compared to the conventional global mustering tool is hardly 3.5%. And in case of publication, if you see here, so growth is exponential increase the number of publication in the laser material processing, and most of what you call publication coming from welding, additive manufacturing, then cutting, cladding kind of thing. But if you see here in market revenue, most of revenue is cutting, and less revenue is welding, then what you call display and other this thing. So cutting is more what you call mature field. So that's why publication is less, but you can market revenue share is high. So now I am going to my what you call one case study is a laser drilling of aero engine component. So laser drilling is nothing but material removal by two mechanisms. One is vaporization, and second one is melt ejection due to high intensity of laser. So I will not go more detail into this what you call energy balance equation and this thing, but if you drill the holes, you can see such kind of feature. So nothing but is a pattern formation, recast layer, heat affected zone, and cracking. This kind of thing you can what you call observe after drilling of the holes. And so here it's detailed laser drilling. If you see, there are a large number of, this is some typical component I am showing here. There are a large number of components need laser drilling. So in a gas turbine application, need for cooling holes in blades, vanes, combustion liner, and south segment, as well as in automotive fuel injection nozzle, fuel filter. Now also in the inkjet printer, that laser is used for drilling of such hole. Then semiconductor industries, printer circuit boards and MEMS and medical application also use laser drilling. So coming to here, source based what you call laser drilling. One can have continuous wave laser as well as the pulse laser. Continuous wave laser mechanism is melt ejection, and if you go shorter plus, you can have the what you call vaporization, ablation, and coal ablation. So in continuous wave laser, CO2 laser is the what you call commonly used for such kind of application. But if you go very short, ultra fast pulse duration, 50-second laser TSFR kind of laser is available. What is happening if you use long pulse and short pulse? The throughput is in long pulse is holes per second. In my lab, I am drilling hundreds holes in a second using NDIAC laser. But same times, I also have 50 seconds. Then I need what you call same hole drilling more than what you call hundreds of minutes. So, but if you see other this thing debris here, tens of micron debris found, but here no debris. Current is a cold ablation. Heat affected zone, you can see in what you call continuous or long pulse duration, but in 50-second laser, there is no. And if you come into depth control, if you want to control depth, is inversely proportional to the material removal rate. Now, here I compare with the some conventional technique, laser drilling. So laser advantage is what you call high speed, non-contact process, flexible, no tool wear, and relatively green. So, but challenge is here, high capital cost, need a backwall strike protection and line of sight process. Some of the what you call you transfer the industrial application, this we have to look into. So generally in our lab or this we use a flat coupon, so we not worry about the what you call backwall protection. I will show in some of my slide why it's important or some component. Then if you see electrical discharge machining, so it's a very slow process and not a green. Electrochemical machining is also poor repetitively and not a green. Electron beam is the one competitive process for laser, but disadvantage is you have very limited geometry here and need a vacuum chamber. and water jet is a need also part in submerged in water. So coming to laser drilling technology, one can drill a hole in a single pulse. It's called a single pulse drilling. Then percussion drilling here need a number of pulses to drill the holes. And third one is a trepanning hole. If you want to drill holes bigger than the beam diameter, you have to just cut it, move laser circumference. So you can cutting up the hole. And then helical drilling, you can remove the hole, drill the hole by layer, layer by layer. So in helical drilling, you can get very good accuracy, and in single pulse, accuracy is very low. But in a single pulse, you can drill a hole in a single shot up to 3 mm, and percussion drilling, you can drill up to hole up to 25 mm thick material, and hole diameter is here less than 0.5 mm, 500 micron. And in this trepanning and helical drilling, you can drill hole diameter bigger than 1 mm, and here drilling depth is limited. Coming to now key process for this drilling, laser drilling. So one is the laser side, other one is the material side, and third one is the processing side. In laser side, so is a very common. So it's for this wavelength, beam quality, beam energy, pulse duration, pulse shape, number of pulses, and repetition rate come into picture. In material side, there optical, thermophysical, and mechanical properties come into picture. And processing side is your focusing optics, depth of focus, focusing position, assist gas, their location, drilling angle, processing speed, and drilling technique come into picture. Now, so here you can see the typical hole drilling. After drilling, what we have to look, hole diameter, taper formation. Generally, laser drilling is not a straight hole. It gives the taper hole, means nothing but your entry diameter is bigger than the exit diameter. So then hole shape, roundness, then spatter formation, recast layer, heat affected zone, microcrapping, and barreling. This is one interesting phenomena happening in only laser-based drilling. Is barreling is nothing but your internal diameter is increasing. Is more than your exit entry diameter, and the in between your diameter is bigger. Is called a barreling. So this is happening due to reflection from the wall of the hole. So this laser is an NDAC laser we use for this drilling application. So it's having a wavelength is 1064 nanometer, power up to average power is 135 watt only we use, and 20 kilowatt is a peak power. Pulse duration we vary from 0.3 millisecond to 5 millisecond, and energy up to 55 joule. And we have different optics for this laser. So some of the application, excuse me. Some of the application need a multi-layer, not the what you call single layer. So it's having some thermal barrier coating. It's a ceramic coating. Then only laser only work. Your conventional technique won't work. You are drilling up what you call multi-layer material. So we use thermal barrier coating is nothing but 7% yttrium stabilized zirconia, and bond coating also there is there, and then different thickness of coating we use for our drilling study. So those are the parameters. So this we also did a numerical analysis of this nickel-based superalloy and yttrium stabilized zirconia, and found that energy of melting for the nickel-based superalloy is less than the what you call ceramic yttrium stabilized zirconia, but energy for vaporization for the what you call nickel-based superalloy is more than the yttrium stabilized zirconia. I will show why that is important for the practical application. So in this we use that as a substrate material, like thermal barrier coated and on the nickel-based superalloy, and drill the holes and measure the what you call entry diameter, it function of the different what you call pulse duration, vary from 0.5 to 3 millisecond, and you can see the hole diameter increase as the what you call pulse width is increased. So more interaction time, so more material removal. So also increase the hole diameter, more what you call heat goes into material, and this is nothing but same thing. If you increase the power, your hole diameter also increase. So we observe a linear relation between hole diameter and pulse width less than what you call 0.2 watt per micrometer square. So here, here actually this sorry here. Is a reverse actually. Here melting is more, and non-linear mechanism we observe lower density. Sorry, is correct. Higher density is more than what you call 2 watt per centimeter. Vaporization is more, and non-linear we observe below what you call lower density, below what you call this sign is this thing 0.2 what you call watt per micrometer square. Melt fraction is more. So so coming to now characterization of this hole, you can see here in a low pulse density, you can see the here micro cracking, and higher what you call pulse energy, you can see the no micro cracking. So we also study the what you call material removal rate. Yeah. So with this thing. So you can see here in ceramic is a need a different, and metal is need a different. So those are the what you call. So we also study the effect of the what you call focal position on the laser drilling hole. So we observe about 2 mm thick what you call about 2 mm focus, you can get the more cylindrical hole. So here a whole laser is what you call diverging, so one can get the more cylindrical hole as compared to what you call focus inside the material. So here more conical hole we are getting. So those are the. Then we also study the effect of gaseous gas on the what you call hole diameter, and you can see the oxygen gives the what you call less taper, due to oxygen give the exothermic reaction, so less taper is there. So we also study the effect of gas pressure on this thing. You can see the higher pressure is remove the more what you call material removal, you can get the less taper. And in practical application, need a hole in what you call angular. So we also drill holes in angle, so we can get the angle holes. So here, but angle holes more problem is what you call micro cracking, and delamination is the issue. So we also solve that. And so in actual component, you can see we use this one of the what you call high pressure nozzle guided fan. So did those kind of hole for what you call cooling application, and is a very complex component. So that's why going to for actual component, we what you call we have to take care of this what you call shape profile, and is what you call close component. So need a what you call burr formation. You have to see how to what you call remove that burr. And third one is what you call after drilling should not what you call damage the what you call second wall. So need a back wall protection. So you can see here after drilling we cut and check their drilling profile and this thing. And so finally we drill the 5 total what you call, if you see the combustion liner is a thermal barrier coating and need more than 12,000 holes. Combustion inner liner more than 6,000 holes, and other components. So 5 engine component we drill and what you call deliver to HL, and now they are having their own production facility of this the laser drilling for different components. So I will not go more detail now due to time limit. So I will go second application is a laser cladding. So cladding is nothing but a deposition of material, you can see here. So we have 3 technique here: powder blown technique, then this coaxial off axis, and also pre-pressed powder. So in coaxial this thing you can see here how is going this laser cladding. So powder is blowing and laser is melting those material and you deposit, and those we are using for also nothing only what you call this thing for what you call repair kind of application. You can see here different repair. We did a 7 pillion housing of the what you call helicopter, then refurbishment of cylinder of this automotive component, and the big shaft, 4-meter big shaft of the air refining shaft also we did. Now this also we did this coating technology for what you call power plant application, burner tip kind of thing application is actually generally this burner tip is our coal feeding nozzle is going damaged due to what you call due to slurry of the coal, and we have to then shut down the power plant and what you call replace those plates. But if you use a laser cladding plate, so this plate we what you call install in actual this NTPC Faruka thermal plant February 2020, and up to December 2023 is intact. In general, if you use this thermal plant, they have to replace every year those plants, but this more than 4 years it withstand. So I will not discuss more detail. So we also coming to, yeah. So in additive manufacturing, so we are having complete ecosystem, not only the printer, but we are having a gas atomizer. So material is very critical. So we are making our own powder. Some of the strategic sector, commercial powder is not available, or what you call, they are not supplying to India. So those powder we are making and using for printing. Then we cannot use a direct what you call this thing, conventional design for additive manufacturing. We are having a design for additive manufacturing. We are design the what you call component and taking advantage of additive manufacturing. Then printing, we are having this powder bed fusion as well as the electron beam melting, as well as we are having very good support of this post processing like hot isostatic press is a unique facility we are having. Then other facility like high temperature furnaces and vacuum furnaces, and very good characterization facility we are having. So one application I will show here that we develop using additive manufacturing. I will go here. So if you want to get advantage, you need a design for freedom, part integration, then what you call conformer cooling channel, dissimilar material welding kind of thing. So this one of the component. So this one is a conventional design of one of the strategic component, and this is the additive manufacturing design. You can see here conventional design weight is 9 kg, but if you design for additive manufacturing, we reduce more than what you call 50 to 60% weight. And you know, any flying component weight reduction is very much important. So those are the different what you call application we develop here. You can see here. Then also this electron beam additive manufacturing is very good for biomedical application. So there whole process is in vacuum and no this thing contamination. So very good for what you call good for biomedical application. And another advantage is this thing surface roughness more, but this is advantage for biomedical application, need a more surface roughness sample. Then we also have state-of-art ultra-fast laser processing. So it's a unique facility. So in this same, in a single workstation, 4 laser beam, different wavelength is coming, 800, 400, 260, 527 nanometer beam wavelength is coming. And pulse duration we can vary from 100 femtosecond to 50 picosecond kind of thing. So using this facility, we developed the application laser surface texturing for automotive application. So texturing is nothing but creating a micropicture on the component. So that the micropicture act as a hydrodynamic bearing effect, then wear particle trap and lubrication reservoir. Then this you can see here, we did on this piston ring and cylinder liner of the automotive component, and we observed more than 16% what you call oil consumption reduction if you use a laser surface texture piston rings. So those are the other components. We also develop this using ultra laser, for example, this cutting of very fine feature in the microwave application, then X-ray tube component, micro heaters, and some ceramic component. I will summarize. So we developed technology for joining, laser cladding, laser drilling, laser hardening, micro machining. Those are the components here. And laser is a very good tool for unmatched precision and capability. So better understanding of laser material interaction could facilitate a minimum feature size beyond the diffraction limits. If you are using a femtosecond laser smaller than the laser wavelength in the nanometer scale, and CLPM developed more than 100 of applications in the last 2.5 decades and promote use laser in Indian industry. So I would like to acknowledge my colleagues, students, lot of people work to develop those applications, and collaborators and funding agency. Okay, thank you.
Thank you, Dr. Ravi. QA session, we are postponing it. Like you can have QA session with that during the lunchtime. Dr. Ravi will be available there.
As a token of appreciation, we would like to present a memento to our esteemed speaker. I request the chair to present a memento. I request Ms. Arti to bring the memento. As a token of gratitude, we would like to honor our session chair, Dr. C.P. Pal. I would like to invite Dr. V. Ganeshan, former director of the UGC DAE CSR, to present the memento, please. I request bring the memento. Thank you, sir. Now let us proceed for lunch. Thank you.
also allowing for C-stack flexibility as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging, in particular it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multifocal microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It is easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
is more accessible and affordable than ever. More and more professionals rely on FLIR's wide range of cameras to reveal invisible heat issues and to capture valuable temperature data. Our own innovation, development, and manufacturing capabilities give FLIR the agility and efficiency to produce such a complete line of thermal imagers and to do it so economically. Volume cameras can be useful in the world of R&D and science. But when it comes to the fine points, researchers and product developers demand the highest level thermal imaging performance, the kind FLIR science cameras are famous for. They need technology that captures high-speed thermal events in high resolution and with the most reliable results to help discover new phenomena, test new developments, and prove findings. They need to record detailed thermal distribution and variations in real time to measure heat patterns, dissipation, and other critical temperature factors. For years, FLIR has been committed to developing thermal imaging cameras that advance research and development projects worldwide. We still are today, with dedicated production and R&D facilities in Sweden and Florida. The FLIR Niceville facility is fully immersed in the design, engineering, and production of cooled cameras. Here, FLIR creates cameras for all wavebands, including near, mid-wave, and long-wave IR, and builds all kinds of detectors, including InGas, INSBE, and SLS. The Niceville team also develops software that is completely tailored to R&D and science professionals. The FLIR Research IR software works seamlessly with all FLIR R&D and science cameras that allows live viewing and provides detailed analysis of the most complex experiments. In Täby, Sweden, engineers in FLIR's state-of-the-art design, engineering, and production facilities focus both on cooled and uncooled cameras, targeted at the most demanding applications. These cameras offer a highly efficient and cost-effective way to capture accurate temperature data. No other thermal imaging company is as committed to researchers and scientists as FLIR. With its dedicated facilities in Sweden and the US, FLIR continues to be the industry leader in cutting-edge infrared technology for R&D and science. You can count on it.
The TPX3 cam from Amsterdam Scientific Instruments is a pinnacle innovation in ultra-fast imaging detector technology. At its core, the detector features a photon-counting hybrid active pixel sensor based on the advanced Timepix3 ASIC developed at CERN. Unlike slower frame-based digital sensors, the TPX3 cam operates using continuous event-driven readout. Each sensor pixel works like a precision stopwatch with an ultrafine time resolution of 1.56 nanoseconds. Activated pixels simultaneously record both the event time of arrival and response duration, or time over threshold, processing up to 80 million hits per second at an effective frame rate exceeding 500 MHz. Individual pixel responses are intelligently filtered by signal intensity and pixel grouping to afford noise-free detection and remarkable contrast. The TPX3 cam is flexibly formatted to detect photons, electrons, neutrons, and molecular ions. Configured for velocity map imaging spectroscopy, the TPX3 cam captures time-resolved images of gas phase reaction dynamics at exceptionally high repetition rate. Combining the TPX3 cam with an image intensifier enables single photon detection for versatile applications in quantum optics, neutron imaging, and fluorescence lifetime microscopy. Dedicated device software provides an intuitive acquisition control interface and data processing workflow. Users are also offered a robust API package for the freedom to customize data management and device operations using popular language libraries. Amsterdam Scientific Instruments' premium detector solutions empower researchers across the world to see beyond limits with unprecedented speed and accuracy. To find out how you can use the TPX3 cam in your research, contact our experts at info@amsins.com.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EPI 2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging, in particular it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter-long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It is easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
Today, thermal imaging is more accessible and affordable than ever. More and more professionals rely on FLIR's wide range of cameras to reveal invisible heat issues and to capture valuable temperature data. Our own innovation, development, and manufacturing capabilities give FLIR the agility and efficiency to produce such a complete line of thermal imagers and to do it so economically. Volume cameras can be useful in the world of R&D and science. But when it comes to the fine points, researchers and product developers demand the highest level thermal imaging performance, the kind FLIR science cameras are famous for. They need technology that captures high-speed thermal events in high resolution and with the most reliable results to help discover new phenomena, test new developments, and prove findings. They need to record detailed thermal distribution and variations in real time to measure heat patterns, dissipation, and other critical temperature factors. For years, FLIR has been committed to developing thermal imaging cameras that advance research and development projects worldwide. We still are today, with dedicated production and R&D facilities in Sweden and Florida. The FLIR Niceville facility is fully immersed in the design, engineering, and production of cooled cameras. Here, FLIR creates cameras for all wavebands, including near, mid-wave, and long-wave IR, and builds all kinds of detectors, including InGas, INSBE, and SLS. The Niceville team also develops software that is completely tailored to R&D and science professionals. The FLIR Research IR software works seamlessly with all FLIR R&D and science cameras that allows live viewing and provides detailed analysis of the most complex experiments. In Täby, Sweden, engineers in FLIR's state-of-the-art design, engineering, and production facilities focus both on cooled and uncooled cameras, targeted at the most demanding applications. These cameras offer a highly efficient and cost-effective way to capture accurate temperature data. No other thermal imaging company is as committed to researchers and scientists as FLIR. With its dedicated facilities in Sweden and the US, FLIR continues to be the industry leader in cutting-edge infrared technology for R&D and science. You can count on it.
The TPX3 cam from Amsterdam Scientific Instruments is a pinnacle innovation in ultra-fast imaging detector technology. At its core, the detector features a photon-counting hybrid active pixel sensor based on the advanced Timepix3 ASIC developed at CERN. Unlike slower frame-based digital sensors, the TPX3 cam operates using continuous event-driven readout. Each sensor pixel works like a precision stopwatch with an ultrafine time resolution of 1.56 nanoseconds. Activated pixels simultaneously record both the event time of arrival and response duration, or time over threshold, processing up to 80 million hits per second at an effective frame rate exceeding 500 MHz. Individual pixel responses are intelligently filtered by signal intensity and pixel grouping to afford noise-free detection and remarkable contrast. The TPX3 cam is flexibly formatted to detect photons, electrons, neutrons, and molecular ions. Configured for velocity map imaging spectroscopy, the TPX3 cam captures time-resolved images of gas phase reaction dynamics at exceptionally high repetition rate. Combining the TPX3 cam with an image intensifier enables single photon detection for versatile applications in quantum optics, neutron imaging, and fluorescence lifetime microscopy. Dedicated device software provides an intuitive acquisition control interface and data processing workflow. Users are also offered a robust API package for the freedom to customize data management and device operations using popular language libraries. Amsterdam Scientific Instruments' premium detector solutions empower researchers across the world to see beyond limits with unprecedented speed and accuracy. To find out how you can use the TPX3 cam in your research, contact our experts at info@amsins.com.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EP2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging, in particular it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter-long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It is easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
imaging is more accessible and affordable than ever. More and more professionals rely on FLIR's wide range of cameras to reveal invisible heat issues and to capture valuable temperature data. Our own innovation, development, and manufacturing capabilities give FLIR the agility and efficiency to produce such a complete line of thermal imagers and to do it so economically. Volume cameras can be useful in the world of R&D and science. But when it comes to the fine points, researchers and product developers demand the highest level thermal imaging performance, the kind FLIR science cameras are famous for. They need technology that captures high-speed thermal events in high resolution and with the most reliable results to help discover new phenomena, test new developments, and prove findings. They need to record detailed thermal distribution and variations in real time to measure heat patterns, dissipation, and other critical temperature factors. For years, FLIR has been committed to developing thermal imaging cameras that advance research and development projects worldwide. We still are today, with dedicated production and R&D facilities in Sweden and Florida. The FLIR Niceville facility is fully immersed in the design, engineering, and production of cooled cameras. Here, FLIR creates cameras for all wavebands, including near, mid-wave, and long-wave IR, and builds all kinds of detectors, including InGas, INSBE, and SLS. The Niceville team also develops software that is completely tailored to R&D and science professionals. The FLIR Research IR software works seamlessly with all FLIR R&D and science cameras that allows live viewing and provides detailed analysis of the most complex experiments. In Täby, Sweden, engineers in FLIR's state-of-the-art design, engineering, and production facilities focus both on cooled and uncooled cameras, targeted at the most demanding applications. These cameras offer a highly efficient and cost-effective way to capture accurate temperature data. No other thermal imaging company is as committed to researchers and scientists as FLIR. With its dedicated facilities in Sweden and the US, FLIR continues to be the industry leader in cutting-edge infrared technology for R&D and science. You can count on it.
The TPX3 cam from Amsterdam Scientific Instruments is a pinnacle innovation in ultra-fast imaging detector technology. At its core, the detector features a photon-counting hybrid active pixel sensor based on the advanced Timepix3 ASIC developed at CERN. Unlike slower frame-based digital sensors, the TPX3 cam operates using continuous event-driven readout. Each sensor pixel works like a precision stopwatch with an ultrafine time resolution of 1.56 nanoseconds. Activated pixels simultaneously record both the event time of arrival and response duration, or time over threshold, processing up to 80 million hits per second at an effective frame rate exceeding 500 megahertz. Individual pixel responses are intelligently filtered by signal intensity and pixel grouping to afford noise-free detection and remarkable contrast. The TPX3 cam is flexibly formatted to detect photons, electrons, neutrons, and molecular ions. Configured for velocity map imaging spectroscopy, the TPX3 cam captures time-resolved images of gas phase reaction dynamics at exceptionally high repetition rate. Combining the TPX3 cam with an image intensifier enables single photon detection for versatile applications in quantum optics, neutron imaging, and fluorescence lifetime microscopy. Dedicated device software provides an intuitive acquisition control interface and data processing workflow. Users are also offered a robust API package for the freedom to customize data management and device operations using popular language libraries. Amsterdam Scientific Instruments' premium detector solutions empower researchers across the world to see beyond limits with unprecedented speed and accuracy. To find out how you can use the TPX3 cam in your research, contact our experts at info@amsins.com.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EP2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging, in particular it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter-long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In a nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It is easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
Today, thermal imaging is more accessible and affordable than ever. More and more professionals rely on FLIR's wide range of cameras to reveal invisible heat issues and to capture valuable temperature data. Our own innovation, development, and manufacturing capabilities give FLIR the agility and efficiency to produce such a complete line of thermal imagers, and to do it so economically. Volume cameras can be useful in the world of R&D and science. But when it comes to the fine points, researchers and product developers demand the highest level thermal imaging performance, the kind FLIR science cameras are famous for. They need technology that captures high-speed thermal events in high resolution, and with the most reliable results to help discover new phenomena, test new developments, and prove findings. They need to record detailed thermal distribution and variations in real time to measure heat patterns, dissipation, and other critical temperature factors. For years, FLIR has been committed to developing thermal imaging cameras that advance research and development projects worldwide. We still are today, with dedicated production and R&D facilities in Sweden and Florida. The FLIR Niceville facility is fully immersed in the design, engineering, and production of cooled cameras. Here, FLIR creates cameras for all wavebands, including near, mid-wave, and long-wave IR, and builds all kinds of detectors, including InGas, INSBE, and SLS. The Niceville team also develops software that is completely tailored to R&D and science professionals. The FLIR Research IR software works seamlessly with all FLIR R&D and science cameras that allows live viewing and provides detailed analysis of the most complex experiments. In Täby, Sweden, engineers in FLIR's state-of-the-art design, engineering, and production facilities focus both on cooled and uncooled cameras, targeted at the most demanding applications. These cameras offer a highly efficient and cost-effective way to capture accurate temperature data. No other thermal imaging company is as committed to researchers and scientists as FLIR. With its dedicated facilities in Sweden and the US, FLIR continues to be the industry leader in cutting-edge infrared technology for R&D and science. You can count on it.
The TPX3 cam from Amsterdam Scientific Instruments is a pinnacle innovation in ultra-fast imaging detector technology. At its core, the detector features a photon-counting hybrid active pixel sensor based on the advanced Timepix3 ASIC developed at CERN. Unlike slower frame-based digital sensors, the TPX3 cam operates using continuous event-driven readout. Each sensor pixel works like a precision stopwatch with an ultrafine time resolution of 1.56 nanoseconds. Activated pixels simultaneously record both the event time of arrival and response duration, or time over threshold, processing up to 80 million hits per second at an effective frame rate exceeding 500 MHz. Individual pixel responses are intelligently filtered by signal intensity and pixel grouping to afford noise-free detection and remarkable contrast. The TPX3 cam is flexibly formatted to detect photons, electrons, neutrons, and molecular ions. Configured for velocity map imaging spectroscopy, the TPX3 cam captures time-resolved images of gas phase reaction dynamics at exceptionally high repetition rate. Combining the TPX3 cam with an image intensifier enables single photon detection for versatile applications in quantum optics, neutron imaging, and fluorescence lifetime microscopy. Dedicated device software provides an intuitive acquisition control interface and data processing workflow. Users are also offered a robust API package for the freedom to customize data management and device operations using popular language libraries. Amsterdam Scientific Instruments' premium detector solutions empower researchers across the world to see beyond limits with unprecedented speed and accuracy. To find out how you can use the TPX3 cam in your research, contact our experts at info@amsins.com.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EPI 2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging, in particular it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter-long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It is easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
Today, thermal imaging is more accessible and affordable than ever. More and more professionals rely on FLIR's wide range of cameras to reveal invisible heat issues and to capture valuable temperature data. Our own innovation, development, and manufacturing capabilities give FLIR the agility and efficiency to produce such a complete line of thermal imagers and to do it so economically. Volume cameras can be useful in the world of R&D and science. But when it comes to the fine points, researchers and product developers demand the highest level thermal imaging performance, the kind FLIR science cameras are famous for. They need technology that captures high-speed thermal events in high resolution and with the most reliable results to help discover new phenomena, test new developments, and prove findings. They need to record detailed thermal distribution and variations in real time to measure heat patterns, dissipation, and other critical temperature factors. For years, FLIR has been committed to developing thermal imaging cameras that advance research and development projects worldwide. We still are today, with dedicated production and R&D facilities in Sweden and Florida. The FLIR Niceville facility is fully immersed in the design, engineering, and production of cooled cameras. Here, FLIR creates cameras for all wavebands, including near, mid-wave, and long-wave IR, and builds all kinds of detectors, including InGas, INSBE, and SLS. The Niceville team also develops software that is completely tailored to R&D and science professionals. The FLIR Research IR software works seamlessly with all FLIR R&D and science cameras that allows live viewing and provides detailed analysis of the most complex experiments. In Täby, Sweden, engineers in FLIR's state-of-the-art design, engineering, and production facilities focus both on cooled and uncooled cameras, targeted at the most demanding applications. These cameras offer a highly efficient and cost-effective way to capture accurate temperature data. No other thermal imaging company is as committed to researchers and scientists as FLIR. With its dedicated facilities in Sweden and the US, FLIR continues to be the industry leader in cutting-edge infrared technology for R&D and science. You can count on it.
The TPX3 cam from Amsterdam Scientific Instruments is a pinnacle innovation in ultra-fast imaging detector technology. At its core, the detector features a photon-counting hybrid active pixel sensor based on the advanced Timepix3 ASIC developed at CERN. Unlike slower frame-based digital sensors, the TPX3 cam operates using continuous event-driven readout. Each sensor pixel works like a precision stopwatch with an ultrafine time resolution of 1.56 nanoseconds. Activated pixels simultaneously record both the event time of arrival and response duration, or time over threshold, processing up to 80 million hits per second at an effective frame rate exceeding 500 MHz. Individual pixel responses are intelligently filtered by signal intensity and pixel grouping to afford noise-free detection and remarkable contrast. The TPX3 cam is flexibly formatted to detect photons, electrons, neutrons, and molecular ions. Configured for velocity map imaging spectroscopy, the TPX3 cam captures time-resolved images of gas phase reaction dynamics at exceptionally high repetition rate. Combining the TPX3 cam with an image intensifier enables single photon detection for versatile applications in quantum optics, neutron imaging, and fluorescence lifetime microscopy. Dedicated device software provides an intuitive acquisition control interface and data processing workflow. Users are also offered a robust API package for the freedom to customize data management and device operations using popular language libraries. Amsterdam Scientific Instruments' premium detector solutions empower researchers across the world to see beyond limits with unprecedented speed and accuracy. To find out how you can use the TPX3 cam in your research, contact our experts at info@amsins.com.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EP2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging. In particular, it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter-long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It is easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
accessible and affordable than ever. More and more professionals rely on FLIR's wide range of cameras to reveal invisible heat issues and to capture valuable temperature data. Our own innovation, development, and manufacturing capabilities give FLIR the agility and efficiency to produce such a complete line of thermal imagers and to do it so economically. Volume cameras can be useful in the world of R&D and science. But when it comes to the fine points, researchers and product developers demand the highest level thermal imaging performance, the kind FLIR science cameras are famous for. They need technology that captures high-speed thermal events in high resolution and with the most reliable results to help discover new phenomena, test new developments, and prove findings. They need to record detailed thermal distribution and variations in real time to measure heat patterns, dissipation, and other critical temperature factors. For years, FLIR has been committed to developing thermal imaging cameras that advance research and development projects worldwide. We still are today, with dedicated production and R&D facilities in Sweden and Florida. The FLIR Niceville facility is fully immersed in the design, engineering, and production of cooled cameras. Here, FLIR creates cameras for all wavebands, including near, mid-wave, and long-wave IR, and builds all kinds of detectors, including InGas, INSBE, and SLS. The Niceville team also develops software that is completely tailored to R&D and science professionals. The FLIR Research IR software works seamlessly with all FLIR R&D and science cameras that allows live viewing and provides detailed analysis of the most complex experiments. In Täby, Sweden, engineers in FLIR's state-of-the-art design, engineering, and production facilities focus both on cooled and uncooled cameras, targeted at the most demanding applications. These cameras offer a highly efficient and cost-effective way to capture accurate temperature data. No other thermal imaging company is as committed to researchers and scientists as FLIR. With its dedicated facilities in Sweden and the US, FLIR continues to be the industry leader in cutting-edge infrared technology for R&D and science. You can count on it.
The TPX3 cam from Amsterdam Scientific Instruments is a pinnacle innovation in ultra-fast imaging detector technology. At its core, the detector features a photon-counting hybrid active pixel sensor based on the advanced Timepix3 ASIC developed at CERN. Unlike slower frame-based digital sensors, the TPX3 cam operates using continuous event-driven readout. Each sensor pixel works like a precision stopwatch with an ultrafine time resolution of 1.56 nanoseconds. Activated pixels simultaneously record both the event time of arrival and response duration, or time over threshold, processing up to 80 million hits per second at an effective frame rate exceeding 500 MHz. Individual pixel responses are intelligently filtered by signal intensity and pixel grouping to afford noise-free detection and remarkable contrast. The TPX3 cam is flexibly formatted to detect photons, electrons, neutrons, and molecular ions. Configured for velocity map imaging spectroscopy, the TPX3 cam captures time-resolved images of gas phase reaction dynamics at exceptionally high repetition rate. Combining the TPX3 cam with an image intensifier enables single photon detection for versatile applications in quantum optics, neutron imaging, and fluorescence lifetime microscopy. Dedicated device software provides an intuitive acquisition control interface and data processing workflow. Users are also offered a robust API package for the freedom to customize data management and device operations using popular language libraries. Amsterdam Scientific Instruments' premium detector solutions empower researchers across the world to see beyond limits with unprecedented speed and accuracy. To find out how you can use the TPX3 cam in your research, contact our experts at info@amsins.com.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EPI 2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging, in particular it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter-long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In a nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It is easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
than ever. More and more professionals rely on FLIR's wide range of cameras to reveal invisible heat issues and to capture valuable temperature data. Our own innovation, development, and manufacturing capabilities give FLIR the agility and efficiency to produce such a complete line of thermal imagers and to do it so economically. Volume cameras can be useful in the world of R&D and science. But when it comes to the fine points, researchers and product developers demand the highest level thermal imaging performance, the kind FLIR science cameras are famous for. They need technology that captures high-speed thermal events in high resolution and with the most reliable results to help discover new phenomena, test new developments, and prove findings. They need to record detailed thermal distribution and variations in real time to measure heat patterns, dissipation, and other critical temperature factors. For years, FLIR has been committed to developing thermal imaging cameras that advance research and development projects worldwide. We still are today, with dedicated production and R&D facilities in Sweden and Florida. The FLIR Niceville facility is fully immersed in the design, engineering, and production of cooled cameras. Here, FLIR creates cameras for all wavebands, including near, mid-wave, and long-wave IR, and builds all kinds of detectors, including InGas, INSBE, and SLS. The Niceville team also develops software that is completely tailored to R&D and science professionals. The FLIR Research IR software works seamlessly with all FLIR R&D and science cameras that allows live viewing and provides detailed analysis of the most complex experiments. In Täby, Sweden, engineers in FLIR's state-of-the-art design, engineering, and production facilities focus both on cooled and uncooled cameras, targeted at the most demanding applications. These cameras offer a highly efficient and cost-effective way to capture accurate temperature data. No other thermal imaging company is as committed to researchers and scientists as FLIR. With its dedicated facilities in Sweden and the US, FLIR continues to be the industry leader in cutting-edge infrared technology for R&D and science. You can count on it.
The TPX3 cam from Amsterdam Scientific Instruments is a pinnacle innovation in ultra-fast imaging detector technology. At its core, the detector features a photon-counting hybrid active pixel sensor based on the advanced Timepix3 ASIC developed at CERN. Unlike slower frame-based digital sensors, the TPX3 cam operates using continuous event-driven readout. Each sensor pixel works like a precision stopwatch with an ultrafine time resolution of 1.56 nanoseconds. Activated pixels simultaneously record both the event time of arrival and response duration, or time over threshold, processing up to 80 million hits per second at an effective frame rate exceeding 500 megahertz. Individual pixel responses are intelligently filtered by signal intensity and pixel grouping to afford noise-free detection and remarkable contrast. The TPX3 cam is flexibly formatted to detect photons, electrons, neutrons, and molecular ions. Configured for velocity map imaging spectroscopy, the TPX3 cam captures time-resolved images of gas phase reaction dynamics at exceptionally high repetition rate. Combining the TPX3 cam with an image intensifier enables single photon detection for versatile applications in quantum optics, neutron imaging, and fluorescence lifetime microscopy. Dedicated device software provides an intuitive acquisition control interface and data processing workflow. Users are also offered a robust API package for the freedom to customize data management and device operations using popular language libraries. Amsterdam Scientific Instruments' premium detector solutions empower researchers across the world to see beyond limits with unprecedented speed and accuracy. To find out how you can use the TPX3 cam in your research, contact our experts at info@amsins.com.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EP2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging, in particular it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter-long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In a nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It is easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
सा वाला करना है?
दोनों ना, दोनों दो स्पीकर
दोनों
है।
दोनों 12 में करना है ना, यही तो मैं पूछ।
3 स्पीकर है ना?
नहीं, 2 स्पीकर।
एक नहीं है क्या?
नहीं, 2 है ना।
एक वाले 3 दिखा रहा था।
नहीं, 2 ही था। हमने एक्चुअली प्रीवियस सेशन में 3 थे।
हाँ हाँ।
इसीलिए एसिमेट्री के कुछ फिगर ने कहा कि हमको इसी समय ही अवेलेबल है, तो इसीलिए थोड़ा हमको उसी हिसाब से सेट करना पड़ा। 12। those who are at the back, please come forward. Come to the front rows, please. After lunch, good afternoon. After lunch, followed by heavy technical brainstorming session. Now we are at the session 12, that is quantum and atom optics. I welcome you all. Now to chair the session, due to some exigencies, our chair has not arrived yet. And now I request convener Dr. S. Satpathy to chair the session on his behalf. I request Satpathy to.
Thank you, Dr. Biswal. Welcome you all again for this session 12. We have two speakers in this session, Dr. Saurabh Datta and Dr. Naveen K. Nischal. Saurabh Datta from TIFR Mumbai and Naveen K. Nischal from IIT Patna. So, first, Dr. Saurabh Datta, and his research interest is the ultra cold atoms and molecules, trapped ions for quantum applications, quantum optics and precision measurements. And he is INSA Young Associate 2024, Indian National Science Academy, and Young Scientist Award 2020. And Beastland Dissertations Fellowships and Carlac Harovic Awards and Purdue University. So now I invite Professor Saurabh Datta, TIFR Mumbai, to start his talk.
Okay, thank you for this invitation, and I'm very glad to be speaking here. So what I'm going to talk about is ultra-cold atoms, molecules, and ions, so precision spectroscopy, and these are all fields which are enabled by very narrow line width continuous wave diode lasers. So before going forward, let me introduce you to my group. So these are the students working with me. I have some postdoc positions and GRF positions available with me right now. Most of the work is actually done by my senior most student, Bhabha, and some of the work is done by Shottabrato. I'm not going to talk about what we are doing with Rahul. So this is what the lab looks like. I'm going to show you the details of this setup later on, but this is the bird's eye picture. This is actually our cold atom apparatus with all its components. So let me introduce you to the most important thing that we use in our lab, which is these external cavity diode lasers. So they are basically semiconductor diode lasers, similar to some things which are available in some of these laser pointers, typically around 5.6 millimeter in diameter. And by changing the semiconductor material, you can have different wavelengths. So if we are looking at, let's say, 780 nanometer, it would be allium, gallium arsenide, and so on. And these are typically, the gain medium is large. So what you do is you take this laser diode, put a collimating lens in front of it, collimate the beam, and you put a diffraction grating, and you try to tune the first order diffracted beam back into the laser, and that is how you establish lasing. And by tuning this angle of this grating, you can tune the feedback that is going, the wavelength that is being fed back, and therefore you can tune the laser's wavelength. And this tuning is done typically using a piezo actuator. So the distance between here to here defines the length of the cavity, but as you can imagine, this is a very complicated system. But it so why is it complicated? So if I look at the diode gain profile, so it's a several tens of nanometer wide. So this is a scale on terahertz. So over a terahertz, it is essentially a flat line. The gain is flat, but then there is a diode which has its own chip, and it forms a cavity because of the size of the chip. So you will see some Fabry-Perot fringes, which is this green line, which is around 100, 200 kind of gigahertz wide. And then we have this external cavity, which has the length between here and here, that gives another cavity, and that has a free spectral range of about 10 gigahertz. So this is this blue line. And then there is a grating feedback, which is around again 100 gigahertz kind of wide. So you have to multiply and see where the gain is the maximum. So in this case, for example, the lasing would happen here. And so you have to control all these different parameters together if you want the laser to tune properly and to have the laser's line width to be narrow. So typically with this, you can get about a megahertz line width, less than a megahertz. Typically we will get around hundreds of kilohertz. So let me show you what, okay, it doesn't move forward. That's good. Yeah, so this is what our setup looks like. So this is the laser diode which we put in some with a collimating lens, and then with some structure so that it is stable. And this is our grating. And with this design, we actually, for a laser around 671 nanometer, we could get around 150 milliwatt of power with a line width around 360 kilohertz. So we could do high resolution spectroscopy. Here you see actually hyperfine resolved spectroscopy of lithium atoms. And this is also the laser with which we use actually to do laser cooling of atoms, which I'll show you later. Just to give you a comparison, with this we built everything with around 6 lakhs rupees, and a commercial system, although you cannot actually buy such a high power laser, but suppose you could, it would cost more than 30 lakhs. So it's a much cheaper solution, and the performance is pretty good, and we can also do it for different other wavelengths. So now I'll come to how we use this laser. So rest of the talk, whenever I'm talking about laser, we are using lasers of this kind. Maybe we are amplifying the laser power with amplifier, but the laser behind it is the same. So first I want to talk about precision spectroscopy. So why are we interested in this? So let's start with the hydrogen atom. So only a proton and electron going around it. Everybody knows that it has this energy level structure, 1s, 2s, 2p, 3s, 3p, and so on. And a dipole allowed transition you could do from 1s to 2p, for example. And people would, if you actually look closer in this 2p state, what you will find is that there is actually, it's not a single state, it splits into 2p 3/2 and 2p 1/2 states with a spacing of 11 gigahertz. So somebody came and had a very nice light source with which they could resolve it, and they could measure this. Then they improved measurements. These are in the 1950s, 40s. And if you go close, you will see that these two states are not also degenerate. There is a small energy splitting around 1.06. This is called the Lamb shift or the Lamb splitting. And actually, and then if you go further, you will see that this 2s actually will split into 2 hyperfine states. And similarly, this 1s will also split into 2 hyperfine states because of the interaction between the electron spin and the nucleus. So the importance is that almost every new step has given a Nobel Prize or led to a new field. For example, the Lamb shift measurement started the development of quantum electrodynamics. So this is very important to do precision spectroscopy. So we do not work with hydrogen, but we work with cesium. But the energy level structure will be the same because cesium also has only 1 electron in its outermost shell. So just to tell you that this is still important, this is a PRL from around 12, 13 years ago. So people are still improving the accuracy of these measurements. They're trying to measure. So in this case, they are trying to measure the 1s to 2s transition frequency. So this, as you see, 1s to 2s transition cannot be done with a single photon. It's not allowed because dipole selection rules do not allow it. So you have to do it with 2 photons. So this is a technique of 2 photon spectroscopy. If you want to do 1s to 2s or 1s to 1d or 4s to 5d, so things which are not allowed by dipole transitions. So for us, we want to study, so this is a cesium, so this is a partial energy level diagram of cesium. Ground state is a 6s electronic state, and it has 2 hyperfine states, F equal to 3 and 4. In a room temperature vapor of cesium, both these states are almost equally populated. We would like to measure, and by the way, the hyperfine splitting is very well known. Actually, that defines the frequency standard or time standard for us. So it's around 9,000 megahertz. And we want to measure the hyperfine splitting in the 7D 3/2 state. So you cannot go from S to D state with a single photon, but so we put basically 2 photons, so 2 photons at this wavelength, 767.8 nanometer. And we go here and then we tune the laser. As I said, the lasers are very narrow line width, so we should be able to see all these features. So we tune the laser and look at the fluorescence when the atom goes from this D state to one of the P states. So, and then we put a filter and look at the fluorescence. So this is typically our setup. We shine the laser from the side, we put a filter and look at this blue fluorescence, and that's how we get a spectrum. Now, since this is a 2 photon transition, suppose there is an atom going here, suppose it is moving towards the right side, and it absorbs 1 photon from a laser which is coming from this side and the other one from the other side, then actually you can see that the first order Doppler shift cancels out. So for the atom sees a higher frequency for this laser and a lower frequency by the same amount. So if you add these two, you see you get 2 times FL, and if this 2 times FL is the laser frequency. If that is equal to the transition frequency, you have a transition and you don't have any Doppler broadening, so you get very sharp lines. So we developed basically a technique to do this very precisely. So what we do is, instead of just measuring on 1 vapor cell, we have 2 vapor cells. One we use to basically calibrate the laser, and the other for the other cell is where we actually record the spectrum. And to record the spectrum, we tune the laser's frequency, and this we do it not by directly changing that piezo that I said, but by changing something called an acoustic modulator's frequency. So, and this you can do very precisely at better than a Hertz resolution. So we can tune the wavelength of the laser very, very precisely, and then we record the spectrum. So what kind of spectrum do we get? So I'm showing you, if you concentrate on this figure, so this you see that there are 4 lines. These are because of the four energy levels over here, and you see I can do this measurement either by exciting atoms from the 6s F equal to 3 state, or I can also do the experiment by measuring exciting from the F equal to 4 state. So I've plotted the spectrum for each of these cases. You see that the height of these peaks are different, but if you measure the splitting, so if you measure the 2-3 splitting in this case versus the other, when you excite from the other hyperfine state, they should be the same. That is what you expect. And the red is actually our data, and on top of that you have this yellow line which is a fit to this data. So this is a very good, so you see that it's a very good fit, and this blue is basically the residual, and the residual is very small. So you see that this is 0.05, this is on a scale of 1. So it's a very small residual, but it will become important as we go on. So bottom line is we can do this very precisely, but we have to do precision spectroscopy, we have to be careful. So what we did is we changed the laser's power, and you will expect some kind of AC stark shift. So we mapped them out, and we could basically cancel out what is the AC stark shift after measuring it, and we can measure at a level of less than 100 Hertz kind of precision these shifts. We also measured how the spectrum changes as we increase the buffer, increase the pressure of the cell. So what is the collisional shift, what is the collisional broadening. So basically these are systematic effects which one has to take care of. So we took care of everything. And then, this is what we find. So what I am plotting here is the hyperfine splitting. So there are 4 lines, so there are 3 hyperfine splitting between 2 and 3, of course for the 73/2 state. 2-3 splitting, the 3-4 splitting, and 4-5 splitting. And on the x-axis is basically that taken over several months. So every once in a week or twice in a week, we take a measurement and plot it on this thing. And this over several months we have plotted. You see that they are very consistent. And this black data is basically the average of all this data, about a year's data. On the left is the data when we excite atoms from the ground state, absolute from the f equal to 3 state of the 6s state. And on the right hand side is when we excite atoms from the f equal to 4 state of the ground state. So as I said, we would expect that the splitting of the 7d 3/2 state, the upper state, should be the same. It should not matter on where we excite from. But what you see is that they are different. For example, here it is 22.08 and it's 22.02. And it is actually on this scale, you don't even have on this scale 22.08. So it's a real difference. So our error bar is around 8 kilohertz and this difference is around 60 kilohertz. So it's a real difference. So what is going on? So let me tell you what is going on. So okay. So I'll tell you what is going on, then next time to explain more. So remember, I'm exciting atoms either from f equal to 4 or f equal to 3. And suppose, for example, let's consider excitation from f equal to 4. The atom is observing going to this manifold of states, and then it can this decay, and this is the photon I am detecting on my fluorescence. But you see, if I tune even my laser to this particular line, there is actually a finite chance that this laser is going to excite the next level or the next level with much lower probability amplitude. And I'm saying it's probability amplitude, not probability. So you have to, what you have to consider is that when I have a laser like this and a detection system like this, there is a chance that atom starts over here, goes to this state and comes down to this state. There is also a probability amplitude of going from here to here and coming back here. So there are different pathways basically through which the atom can start from f equal to 4 here and end up in this final state. So it's like interference Young's double slit or a Young's multi-slit experiment. So I start from some initial states. I can have different probability amplitudes of going through different states and ending up with the final state. And therefore, like Young's double slit, we will have interference. So what is happening is, although we are detecting fluorescence, there is an interference effect. So actually, we can do these calculations of all these transition metrics. I will not bore you with the details, but we can actually calculate what is the line shape for this if we consider this effect of quantum interference. And I will show you how the experiments match with our data. But before that, let me give you the summary. When you do these calculations, what you get is the following. So suppose in this cell you are sending your laser in this direction, and I am detecting in this perpendicular direction, and my laser is along this green line, epsilon L cap is the laser polarization. So you can define an angle between the detection axis and this laser polarization theta, and what we find is that this line shape depends on this angle theta, and only at a very special angle, which is when P2 cos theta goes to 0, or when theta is this magic number 54.7 degree, this interference that I said all vanish. So therefore, your line shape actually becomes your Lorentzian or your Voigt line shape, which is the standard line shape we use for fitting. But at any other angle, there is interference effect, right? So here is what the data which shows that. So this is basically what we had earlier in our. This is where we had our earlier experiments. In this case, now the black is the data and the gray is the fit to a Voigt line shape. And here I have the residuals, which is now zoomed in more. You see that the residual has a pattern. It is asymmetric. It is less on the left. It is lower than 0 on the left-hand side of this peak, for example, and higher than 0 on the right-hand side of the peak. On the other hand, if you do this close to the magic angle, you see these residuals have become more or less flat, symmetric around the center position. If you change to 90 degree, you see the residual sign have sort of inverse. So now it is higher than 0 on this side and lower than 0 on the right-hand side. So we can now do a very detailed comparison between the experiments and theory. So this top part is our experimental data, and below is the theory with no free parameters, and the theory is the line shape model that I told you. So for example, here is again the red data fitted with a Voigt line shape, which is the yellow thing, and this blue is the residual. And we do the same thing for the theory. We find the theory line shape and fit it to a Voigt profile, and we plot the residual. So the residual has this kind of pattern in theory, and you see the experiment has a similar pattern. Similarly, you can see if I excite from f equal to 4, this is the residual pattern in the residual from experiment. This is what is from theory. Now in theory, around as I said, around 54.7 degree, there is no pattern in the residual, and theory there is no noise, so you don't see any noisy things. But here you have noise, but you see that the asymmetry has vanished. And if you go to 90 degree, you see in theory there is a reversal in the residual pattern of or the sign reversal of the residual, which is also there in the experiment. So basically, looking at the residual of the fit, we can say actually whether there is interference or not. And at this magic angle, you don't have interference. What this means is that when I plot this hyperfine splitting at different angles of this theta, you see this was the first data point, 0 degree was the earlier difference we saw, which is at 22.02 and 22.08 when we measured from ground f equal to 3 versus f equal to 4 state. But as we go to the magic angle, this difference vanishes. If we cross this angle, again the difference shows up. And this is consistent across different hyperfine states. Also, we have done experiments on the D 5/2 state where we have a similar pattern. So what I want to take, what I want you guys to take away is that the excitation laser is not a broadband laser. It's a very narrow line width laser, which is very much narrower than the hyperfine splitting of the excited state, but you can still have excitation to other levels, and there is a probability amplitude of doing that. And although we are detecting spontaneous emission, the interference survives. So spontaneous emission does not kill interference, so we have to take care of this thing. So after we do this, this is a summary plot of what we measured. So this is our measurement with this error bar, and this is compared to other people. So we improve on this hyperfine splitting measurement by a factor of 20. So this is what I had to say about precision spectroscopy, and I'll now just switch to this cold atom part briefly. So, why are we interested in this cold atom physics? One is, of course, if you go to very cold temperatures, we don't have Doppler broadening, so you can have very nice spectral narrow features like we had for this 2-photon spectrum, right? The other important thing is, suppose I want to prepare the system in a very well-defined state. So suppose I have a molecule, I want to prepare it in the ground rotational state. You see typical rotational spacings are around 0.4 micro eV. So if you convert to temperature, kBT, it will be around 5 millikelvin. So if I am above 5 millikelvin, then molecules will be distributed over large number of rotational states. So if I want a single rotational state, I have to go below this temperature. So typically, using laser cooling, you can go to much less than a millikelvin, and it basically allows you to prepare systems in a single quantum state. So what kind of experiments can you do? I'll give you one example. So if you consider this reaction, so this is potassium rubidium molecule, this is a real molecule, and if you have potassium rubidium in a gas and they collide, actually this gives an exothermic reaction, and it makes a potassium dimer and a rubidium dimer. So at room temperature, it is an allowed reaction because it's exothermic. But if you go to less than a microkelvin, actually this reaction stops. That is because if you prepare all the potassium rubidium molecules in a single quantum state, actually these molecules are fermionic, right? So you know that if I prepare all the fermions in a single state, then they cannot collide because there is Fermi exclusion principle. Two fermions cannot be on the same place, right? So actually at very low temperature, what is this L equal to 0 or head-on 0 partial wave collisions are completely forbidden, and L equal to 1 is the first partial wave collision. That would be allowed, but there is a barrier because of Schrödinger's equation basically, which is around 24 microkelvin high. So atoms, the molecules do not have enough kinetic energy because they are at 1 microkelvin. So they cannot climb this barrier. So they cannot come close enough where the reaction can happen, and therefore the reaction stops. So you can turn a so-called exothermic reaction, and you can stop it by basically doing a quantum state control. So our lab looks at trying to make different kinds of polar molecules. And the reason we are interested in this kind of polar molecules is that people know how to put atoms in what are known as optical lattices, which you can make by interfering laser beams. So if you have a 1D standing wave of laser, people have worked on this for many years, that the atoms go and sit at the highest intensity point in the laser. So you can have a 1D standing wave, you can have a 2D standing wave, so you can have a structure like this where the atoms will go and sit on these antinodes, and you will have a very nice crystal of atoms, and these are called optical lattices. But the problem is with atoms, the interaction between atoms is very low. So these are almost non-interacting systems. So but if you can put polar molecules which interact by dipole-dipole interaction, then even two molecules sitting in two different lattice sites, which are around half a micron apart, there is significant interaction. So what you can do is you can simulate long-range interacting systems if you put polar molecules in optical lattice. So the first challenge is to actually make these polar molecules. They are difficult to make, and actually you cannot start with a molecule and laser cool. You have to start with typically with atoms and then make molecules. So this is what we are trying to do. So I also introduce another thing which is there in the same apparatus, which is an ion trap in the apparatus. So these are this what we have is a linear Paul trap, and we have few varieties of them. So the most standard one is this linear rod kind of Paul trap. So you can apply RF voltages and you can trap ions here. You can also apply lasers and laser cool them. And the kind of work you can do when you have this kind of trapped ions and also trapped atoms or trapped molecules is look at collision rates. So let me give you an example. So here is a crystal of laser cooled calcium ions from a group in Switzerland. And you see, as time goes on, the number of ions are reducing. That's because they are allowing the crystal to react with rubidium, cold rubidium atoms, and therefore some of the calcium is getting transferred to calcium rubidium plus, and there is also a charge exchange reactions which gives you rubidium plus. So before reaction, this was their mass spectrum with only a peak at the calcium expected calcium place, but after reaction around this 100 seconds, they have peaks at different places corresponding to different molecular ions, so cold molecular ions. So you can now, doing these experiments, you can actually measure reaction rates at very low temperatures, and you can tune the temperatures for example, you could have relevance in astrophysics where in outer space this kind of temperature is very prevalent. So how does this work? I think everybody knows here, but so we typically work with cesium and lithium. For laser cooling, we tune the lasers to this laser cooling transition. So this is a closed transition from f equal to 4 to 5. So the atom, if it is moving, it absorbs many photons, typically 10 to the power 6 photons per second. And every time it absorbs a photon, it gets a small momentum kick of h bar k. And therefore, after repeated absorption, it slows down almost to standstill. And typically, what you do is this is a one-dimensional cooling, but if you put lasers from all 6 directions, then actually even if the atom is moving in any of the directions, it will see this laser, and due to the photon's momentum, it will cool down. So what happens in this is occasionally the atom falls out of the cycling transition and it comes down to this f equal to 3 state, but then we apply a small weak laser which is called a repumping laser, and we pump it back. So you go to f equal to 3 to 4, and then from there it comes back to f equal to 4, and then the cycle continues. So this repumping is needed for laser cooling to work. So once we have these atoms, this is for cesium I said, but we can do a similar thing for lithium. The wavelength is different for the laser, but the same process. And suppose I have 2 atoms, let's say A is lithium and B is cesium. We allow them to collide, so we have cloud of lithium, cloud of cesium. They collide, and we apply a laser which is called a photoassociation laser, which makes a free to bound transition, and you make a molecule in the excited state. And this you can tune by changing the density of these atoms, by increasing the intensity of this laser, and by changing this overlap, wave function overlap, which you can change by tuning your laser, because that depends on the quantum state in which you are forming the molecule. So this is one way to make molecules, and this is one of the process we are trying to do. So let me now show you our apparatus. So this is the central part of the apparatus. This is a UHB chamber at 10 to the power minus 11 millibar of pressure. This is where in the center of this is the 6 beams for making this what is known as the laser cooling and magneto-optical trap. And we have a cesium 2D mott here, 2-dimensional mott, and this is our Siemens lower, and the backside is a lithium oven from which we source our lithium atoms. So this is the top view of the schematic of the apparatus. So this is where we trap the atoms. Actually here inside this we have also our linear Paul trap, and therefore we can trap atoms and ions in the same place. So if I look at the center, this is a real picture of the center part of the chamber. These are the rods for the linear Paul trap, and this is where actually my atoms are trapped using laser cooling, and also the ions using this RF, applying RF on these rods. We also have an Einzel lens and a mass spectrometer in this direction to do mass spectrometry on this. So if we form a molecule, suppose things collide and a different species is formed, we will be able to detect it by doing mass spectrometry. So this is a picture of our lithium magneto-optical trap, this small blob here, taken with just, you can see it with your naked eye actually. This is a cell phone camera picture. And this is a cesium cloud. We typically have around few times 10 to the power 8 atoms at temperatures of around 200 to 300 microkelvin, so less than 0.5 millikelvin. So what kind of experiments can you do with these things? So I'll give you two examples. One is you can do atom-ion collisions. So what I've shown here is at this time, 10 seconds, I'm allowing my cesium atoms to load. So it loads and then atom number saturates. At this point, I have turned on my photoionizing laser, which ionizes some of the cesium atoms. Therefore, the steady state atom number becomes lower. And at this point, I have turned on the ion trap. So whatever ions were getting created are now trapped in the ion trap. And these ions collide with the atoms and throw away some of the atoms from the trap. Therefore, there is a further reduction in the number of ions. And from this kind of measurements, actually, you can find out what is the atom-ion collision rate. So, and this is what we have done, and details are in this paper. We have also seen that we can sympathetically cool ions using atoms. So, and one signature is that if you look at how long the ion survives in a trap, so this black data is when there is no coolant, and the red data is when we put cold, laser-cooled atom in with the ions, and you see the ions lifetime has increased, and this is a signature of ion cooling by atoms. We have also studied collisions between cesium atoms and lithium atoms, so now neutral-neutral collisions. In this case, again, the black data is when we have loaded our trap and then we stopped our sources. So what happens is over time the atom number gets reduced. So the black data is when we just let it get reduced on its own, and the red data is when we actually, on top of a cesium mod, we actually add a lithium mod. So, and the reduction is faster. This is because lithium atoms and cesium atoms are colliding, and the cesium atoms are being thrown out of the trap, and therefore the decay is faster. And we can study this decay, what is the rate, we can measure that, and here is a plot of what is the cross, sort of this you can think of as a cross section as a function of excited state population of cesium. So on the left hand side there is a lot of population, and as we go to the right there is very little excited state cesium population. And you see that the reaction rate actually, or this collision rate coefficient of the cross section depends on the fraction of the atoms in the excited state. So just why is this? So the explanation for this is the following. Suppose this A and B, lithium and cesium, are colliding in the ground state, but I excite some of this B to the excited state, so it becomes B star. Here actually they form a collision complex. They could also form a quasi-molecule, and then they can decay back to a ground state molecule, or they can decay to some dissociating states. But these traps are very specific. They can only trap some certain kind of atom. So if it's a cesium trap, it only traps cesium with a very low kinetic energy. So whether it forms a molecule or a high kinetic energy atom, the atoms basically escape. So therefore, both these processes lead to loss of the atoms, and this is what we are seeing. So, but if I completely sort of can remove the population in this excited state. So if there is no B star, then I should not have this loss. So this is my last slide. So I can do this in my experiments. So the reason I had my population in the excited state is because I had this cooling transition which was putting atoms in this F equal to 5 state of this 6p state. Now remember I told you a repump laser. So if I switch off this repump, what will happen is laser cooling will work, and if the atom comes to this F equal to 3 state, then everything will get accumulated here, and there is no other laser to pump it back. So I will end up with atoms in a quantum state controlled F equal to 3 state. So in a regular mod where the repump is present, I see an increase as I start my laser cooling, I see an increase in the number of atoms or the atomic fluorescence, and then it saturates. But if I have a geometry where I block this center part of the repump, so if the atoms are here, they don't see this repump. So what you see here is that there is hardly any rise in the fluorescence, But if you actually suddenly fill in with a repump, you put an additional laser, then you actually see there is a jump. So there are atoms, but they are not fluorescing. That's because everything is in the ground state. So if this is the case, if we can prepare this in a dark state, and sorry, this was the second light. This is the last slide. So this blue data is a number of lithium atoms we can load when you have a bright or a regular cesium mod. It's a very small number of atoms we can load. But if we go to a dark cesium mod where all the population is in the ground state, you see the lithium nicely rises. So this black data is the number of atoms we can load, lithium atoms. And for comparison, this red is the case when we don't have any cesium atoms. So it's only lithium alone. So we are almost as if this lithium doesn't see that there is a cesium atoms. So this basically shows that we can load simultaneously around 10 to the power 8 lithium atoms, and as I said, we also have 10 to the power 8 cesium atoms. And they are co-trapped in the same space, so there are two clouds which are overlapping. So now we are going to, hopefully in the next 6 to 8 months, we are going to try to associate these atoms, lithium and cesium atoms, and make molecules out of them. And these will be polar molecules. Actually, lithium cesium is the most polar molecule among all bioalkali species. So with that, I will thank you for your attention and take questions.
Thank you, Saurabhji, for nice talk. Session is open for question and answer. Any question?
At 670 or what is the wavelength of that, and for rubidium like
we
other
have lasers, right?
Lasers, yeah.
So we have made at 670 for lithium, 852 for cesium, and 780 for rubidium. So these are 3 wavelengths we already have.
So for 2 wavelengths, like 2 molecules, you are trying lithium and the cesium.
Yeah, lithium needs
so both will require different wavelengths actually.
Yeah, lithium needs 671 nanometer laser. And cesium needs 852.
So both lasers you will be working together?
Yeah, so we have 2 separate lasers.
2 separate. Okay.
Yeah, so and the design is the same. So what I showed you, that was the example for the lithium laser 671, but the cesium laser at 852 are the same design.
So for trapping this cold atom things, you will be applying both the lasers?
Both lasers together. So we have combined both the lasers through beam splitters and send them to the chamber.
Okay.
Yes.
Any other question? Sir.
I was just curious, what kind of physics you can expect when you want to do this interaction of this molecule?
So you can do...
Because effort is so much, I just want to know what.
Yeah, so for example, you can basically study long-range interacting systems. So the idea is that it is very difficult to compute in a computer if you have long-range interaction, because you cannot truncate the series. So it's a 1 over r to the power 3. So so typically it is easy to calculate when you say that only there is a nearest neighbor interaction. But these systems, they have nearest neighbor, next nearest neighbor, and so it's a 1 over r to the power 3 scaling. And truncating, people have seen that truncating does not give you a result which agrees with experiment. So,
but at your own institution there is quantum computers. So don't try the quantum computers. There will be the ideal cases for doing this kind of long range interaction.
Yeah, but these quantum computing
in
India.
I'm not caricaturing, but in generally quantum computers are basically meant for this.
Yeah, but with only 2 qubits, 3 qubits, you cannot do long range interaction.
No, but it is available now. Source will be Google
is
giving.
With those maybe it is possible. But actually, one thing is that whether all these 100 qubit quantum computers are actually quantum computers is still debated.
So that's a good debate, because then this kind of effort will not be required.
Yeah.
Thank you very much.
True.
Any other question? Okay, if there is no questions, let's thank Saurabh Datta again.
I request the chair to present a memento to our esteemed speaker. I request Vishali to bring the memento, please. Thank you.
Our next speaker is Professor Nabin K. Nischal, Indian Institute of Technology, Patna, and his area of interest is applied optics, optical information processing, image encryptions, watermarking, digital holography, and fractional Fourier transform based signal processing, correlations based optical pattern recognitions. And scientific recognitions, world's top 2% scientist list by Stanford University and LCB are considering, Indian's top cited author award 2019, and fellow International Society of Optics and Photonics, editorial board members, optical engineering. So, welcome Professor Nabin K. Nischal for his exciting talk. His talk is measuring topological charges of an optical vortex beam.
A very good afternoon to one and all here. Before starting my talk, I must thank the conference organizers and basically Dr. Satpathy and my most and very good friend of mine whom I am meeting after 20 years, Dr. Ajit Upadhyay. We did PhD together from IIT Delhi and we know each other from PhD days. So it's a good occasion to meet not only my friend with many of you. My talk is a little bit different from the previous talks and the other talks which we have been listening for last 2 days. I work in the area of classical optics. So basically it is mostly focused on classical optics part. So outline of the talk will go like this. I'll talk about structured light. Then within structured light, I'll talk about vortex beams, how such beams are generated and how such beams are measured. What are the applications we can work on? Optical vortex lattices means once you have more than one singularities and then it forms the shape of a lattice. Optical correlation architecture we use for measuring them and how these topological charges are measured. At the end, I will talk about my own research topic also, another area which I have been working for many years, that is on optical cryptography or optical security, how to secure data. So when we talk about structured light means we can play with the properties of the light, we can play with the amplitude, we can play with the phase, we can play with the polarization of the light, or these parameters can be tailored as per our own wish. How do we wish to use such kind of optical beam? This is what we call as the structured light. One of the basic examples of the structured light is the Young's double hole experiment. Once we perform this experiment, we look at the fringe pattern, bright and dark fringe pattern, which is also a kind of a structured light. So how to generate such kinds of light where you have the control of these three parameters, amplitude, phase and polarization. So we have the methods based on diffractive optical elements, means diffraction. We can use spatial light modulators. Once we generate these kinds of beams, how to measure these kinds of beams and their properties. For that also we use the interference method, polarization method and diffraction method. And applications can be and are in optical manipulation, optical imaging, optical metrology, optical cryptography, quantum cryptography and so on. So we start with this optical singularity first. Singularity happens everywhere. We have the singularity in nature as well. These are the examples of the singularity happening in nature. So these types of optical singularity is of phase singularity, it can be our polarization singularity. So optical fields with singularity have a spatial inhomogeneity. When we talk of the polarized beam, so polarized beam is of two types. One we call as the scalar beam of light, another one we call as the vector beam of light. Scalar beam of light means the state of polarization is uniform across the field, and vector beam of light means within the cross section the state of polarization is inhomogeneous or different. So this is the example of the phase polarization. Once we have this phase polarization and such beams, this is how mathematically we express them, and we can look at these kinds of phase polarization, phase singularities. So singular point where the phase profile of the light, how does it look like? Then we have polarization singularity. In polarization singularity, we have this state of polarization of at each spatial point in the transverse plane is different, can be represented by this polarization ellipse where you have this ellipticity angle and azimuth angle to control. This is how we look at, and the polarization, a singular point in the polarization distribution of the light, what you can look at. So we can generate these kinds of beams, and within this polarization singularity again we have different types of beams, what we call as the C type, V type beam. This is because depending upon the state of polarization how they behave and how they stay when they are within that beam. So we have this optical vortex beam represented by this expression, where this exponential term IL phi is the most important parameter. Under this IL phi, L is denoted as the topological charge of the beam. This is not a charge, but it takes the value of, it has the value of positive and negative, and it can be fractional also. So the examples of the Lagrange-Gaussian beam or the Bessel beams, we have these two cases. So I will skip this part. This is how the polarization distribution will look like when you have this vector beam. You can look at the ground field. It has all types of polarization states within its cross section. So when we look at these types of singular beams, singular beams means light beams embedded with the singularity. So they are classified into two types: vortex beams, which is basically a scalar beams, and vector vortex beams, which is basically a vector beam. In that case, the polarization singularity carries both phase singularity as well as polarization singularity in both the cases. So how to generate these kinds of beams? So for generating, we use a liquid crystal spatial light modulator for the purpose. The basic requirement for the kind of spatial light modulator is it should be able to display 0 to 2 pi phase, and then we control the phase. We display desired computer generated hologram onto the SLM, and then we control the beam, and then we generate these kinds of beams. These are the examples what you can see with the different topological charges. So through this technique we can generate the optical beams having different topological charge. This is also called as the OAM beams, orbital angular momentum beams. And we can generate these kinds of beams with the different amount of topological charges. These topological charges, it can have, as I said, it can have positive value, negative value, or fractional value. So positive and negative, it only tells you about the counterclockwise or anti-counterclockwise status. It doesn't mean, the minus sign has no meaning otherwise. And if the L value is large, then the central region, dark region size will become larger. So now the point is how to detect these kinds of beams. So determination of topological charge has advantages, like it confirms the presence of the optical vortex. It means the optical vortex is existing in that beam, and also it gives the order of the singularity and associated orbital angular momentum. So like you can see the example of the two examples of TC1 and TC2. So what are the two methods? Two methods are diffraction based methods. So what we do in diffraction based methods, we generate an unknown vortex beam which we made to pass through the specially designed phase mask. So phase mask we digitally design and display it onto the SLM. And then the resulting diffraction pattern is analyzed, and through that analysis we come to know what is the topological charge, 1, 2, 3, 4, whatever it is. Interference based method is an unknown vortex beam is made to interfere with the reference beam, and resulting interference pattern is analyzed, and then we come to know what is the topological charge. So interference based method is a bit simpler method than the diffraction based methods. So here you can see the examples. So by beam 1 and beam 2, you can see that with the plane beam we are generating the interference pattern, what you look at the interferogram. Second case is you have the beam 1, beam 2, third one is again beam 1, beam 2. 3 cases you can see. In all the cases we look at this pattern what we have generated through the interference, and what is the number of times -1 gives you the topological charge. Then we developed other techniques where we can use self-referenced interferometric methods for determining the topological charge of a vortex beam. So then we have various variations into it. So interference with a laterally displaced replicated beam. In one of the beams we introduce tilt, and we look at the interference pattern, and then we count the topological charge. Then we tilt orthogonal direction to the displacement, then with difference in curvature. So these are the techniques how we create these kinds of beam, and we can count the number of these patterns, and we can say what is the topological charge. So interference using a conjugate replicated beam, again we will get this kind of a fringe pattern, and we can count the pattern and tell the topological charge. More details you can see in these papers. So up to this we are able to generate these kinds of beams, and we use these beams for our security purposes, security applications. Then it came to our mind that can we develop or generate these kinds of beams with normal LED light instead of using a laser light. So we replaced that laser light with a partially coherent beam like an LED light, normal LED light, and we could do that. So I'll skip the mathematics part for the sake of time, and I'll show you the experimental setup. This is the experimental setup what we have used for generating them. The procedure is same what we mentioned earlier, and these are the results. So here you can say we have generated this kind of beam, array of 16 vortices you can see in the first result. Then the second one with the topological 16 vortices, topological charge is 20 using a green LED. Then second you can see array of 64 vortices, topological charge value is 10. Then experimental results, and these are simulation and experimental results, all for any kind of pattern we can generate. Some more results with the green LED and red LED. And then once we have generated these kinds of beams, then we had to see that when you are generating an array of these kinds of vortices, vortex array what we say, or vortex lattice, so how to measure these kinds of beams and topological charges. Now it is possible to have these topological charge values in fraction. So fraction means this topological charge 1 means it has 0 to 2 pi complete one rotation. If topological charge is 2 means within one rotation it has 2 values. So it can take fractional values as well. So for measuring the fractional values we had to develop a technique how to measure the fractional topological charges. So what we did, so we used this geometry for this similar geometry for the interference pattern. So like topological charge is 10 or topological charge is 10.5. So what we look at, we zoom that portion, we look at this parameter R. We calculated the R with the formula what we have developed, and from there we look at the zoomed part and calculate this topological charge. So we can, in the fractional case, not only 10.5, we can calculate or measure accurately any fractional topological charge value, like you can see here. 10.25, 10.45, 10.65, 10.85, and so on and so forth. So this is the futuristic technique that for the optical communication purposes or free space communication, we always require this orthogonal polarization states of the light beam. Usually this left polarized light beam or right polarized light beam, they are orthogonal to each other. So we are looking at the larger number of orthogonal cases, and such beams have these kinds of orthogonality. It will have minus L value will have -1 or +1, so they are orthogonal. So similarly, we can have minus 0.1, minus 0.5 to plus 0.5. So we have so many orthogonal states, infinite orthogonal states. So that is going to give you the boost in the optical communication applications. Some more results what you can see for different fractional topological charges. For this topological charges, we were looking for a better, this is a little time consuming process, so we are looking for a real time application oriented process. So we use the concept of optical pattern recognition. So quickly I will explain. The optical pattern recognition technique tells you that if we are looking for a known pattern out of the unknown scene, so this technique tells you that you can, where this scene is there, this object is lying. Like out of these tank images, we are looking for a particular tank, so where this tank is, we will get an correlation output, and that confirms the position or confirms the type of the object we are looking at. This can be used for any applications. So there are three approaches for working of this application. One we call as the Wonderlook correlator, then joint transform correlator, and third one is the hybrid correlator. We use the concept of hybrid digital correlator for this purpose, and combined and applied that correlator approach for getting to know about these kinds of optical vortices or determining the topological charges. These are the geometries what we use for calculating or for computing the optical correlation. This is the Wonderlook geometry, and this is the joint transform correlator geometry. Third one is the hybrid correlator, in which half part is done digitally and half part we do optically. So we use one SLM to display the function, and one Fourier transforming lens that gives you the Fourier transform and final result. So if there is a correlation peak, that confirms the identity, and if the correlation peak is missing, that means it is not there. So it has several advantages for doing that. So I will skip these part. So this is how we do. We have this is the general method how do we perform these kinds of operation. So we have some tank images, then we calculate its Fourier transform, display it, and we generate a filter. There are various filters we develop for the purpose. And this filter development is itself a very challenging task. It means if we have to identify an object which is rotating. So this is one type of rotation. Second problem is if you are looking at an object which is at a longer distance, then there will be a scale variation. So image size will be smaller or larger, but you have to identify it correctly. Third problem becomes if it is rotating out of plane. So you are looking at the object from one side or the other side, it can take any angle. So 0 to 360 degree, any angle it can take. The complex problem can be complications will be very much when you have a combination of all these problems. So then it becomes very difficult. So we developed a filter for the purpose, and that we use. This is what we call as the maximum average correlation height filter. I'll skip the basic part. And then we applied this concept into our topological charge determination. So initially we applied it for only calculating the integral values, not the fractional values, and then we have calculated it for the fractional values as well. So here you can see if you are looking at the topological charge value 5, then we have a correlation peak here. Looking at 18 or -23, where the topological charge value we are looking at, we will get a correlation peak there, and that confirms and that this is the topological charge value. So this worked very well, but when we are looking at this is the very simple experimental setup, and that combines this correlator output and for the generation of the optical beam. This we can use for any values. So worked in all simulation as well as the experimental results. experimental results what you can see there. But this method worked very well for all the integer values, not for the fractional values. In the fractional values, it became very difficult to calculate that. We further added our research into that, and we could calculate the fractional topological charge as well through this optical correlation approach. So I'll show you the experimental result directly. This is what the fractional topological charge value is. So if the topological charge value is 7, how does it look like, and 8, how does it look like? In between we have 7.5. So we'll look at the 7.5 values, look at these values at every step of 0.25, 0.2, 7, 7.2, 7.4, 7.6, 7.8. So you can look at the intensity pattern is changing. So in the correlator basically matches the intensity pattern. So exactly it gives you the where the match is there. And through this match we could calculate the topological charge any value from 7 to 8, and it works very well. And it is very exact. When we were submitting this paper, we received a comment from the reviewer that how does it, whether it will work better than the machine learning based methods. But in case of machine learning based methods, you have to have a large data set for training the data. Here we don't require any training data. No training data is needed, and that is why it works, it requires less data basically, no data. Any data you have, we can calculate it very nicely. So this is what the experimental setup is. This is how the experimental result is going to look at, and we can exactly locate the location of the peak also. So it gives you these kinds of results for all the cases. So further, not only to that end, we started working on whether we can track these correlation peaks, and it means track the vortex. So for tracking also, we use this same concept of optical correlator, because this optical correlator is famous for tracking applications. So we use this concept for the tracking. This is the experimental setup what you look at, what you see here. We have to use 2 SLMs for the 2 purposes, then other components, and then we can track them. So we have the light beam, introduce the helical phase. Helical phase is again introduced through the computer generated hologram. We display it on the SLM. This is how the topological charge is tracking along x-axis. Unfortunately, this video is not working. It tracks basically along the x-axis, and the below one it tracks along the y-axis. Very accurately we can we track these results. So I think this is all for what I wanted to talk about the optical structured light and how to measure the topological charges. Next I work on the optical security area. So I do not have much time to talk about, but just I wanted to let you know that the optical security research work started in 1995. And in 1995, the authors, Professor Javidi and Refrigier, they published a paper in Optics Later. That paper has today more than 6,000 citations. So it is 30th year of that paper, because I published in 1995, this is 2025. So again, the researchers across the world, they came together and they have written a paper which will appear soon in the IEEE Access. It is on the roadmap on optics and photonics for security and encryption. So there are 28 leading authors across the world from 21 academic institutions and 9 countries. This will appear soon. I am one of the co-authors of this paper. So just to conclude, I talked about optical cryptography, demonstrated the vector beam generation method and how this array is generated. I missed this crypto system part because of the time. So I must acknowledge my PhD students who are working together and whose result I am sharing with you, and funding agencies, because without fund nothing can work. And thanks very much to all the audience who has patiently listened my talk. Thank you so much.
Thank you, Navinji. You completed in time.
Thank you.
The session is open for discussion. Any question?
If there is no question, it is good. Oh, you have a question. Yeah, you can speak loudly. You can speak loudly, no problem. It is related to?
The angular momentum of the photons in the regular version mode.
Yes.
So, recently I read a paper regarding ring boside cell condensate, where they make a ring using cold atoms. So, in principle, if you transfer this angular momentum of the regular version mode to that ring, it will be transferred in some quantum. So, the topological charge should change because some of it has been transferred to the ring in the rotational form. And the beam which comes after it will have some different topological charge. So can we measure this change using whatever method you have suggested in topological charges?
No, you, in any case you can measure the topological charge through this method. But I am not sure whether about that technique what you are mentioning. I don't know about that. But in any case you can measure the topological charge. It is irrespective of where you are using. Wherever you have the OM beam, it is carrying topological charge, you can measure its topological charge. Anywhere. In principle, it should work in your case also. But one has to walk and check. Yes?
There.
Yeah, please say again.
Using LED, I mean, can we generate a topological charge of order 1?
Yes.
Only 1?
Yes.
And how stable it is under propagation? I mean, because these are partially coherent beam, right? So, I mean, how stable it is?
Yeah, it is stable. It is stable. We have checked in our laboratory setup. We have checked up to 50 meter distance. It works well.
Okay.
And in 50 meter, we also worked for the communication purposes. We introduced the different phase or variations, because basically the atmospheric turbulence we created, and then we allowed the light beam to propagate. And then we checked at 50 meter distance. It worked well. But there is a problem with the fractional topological charges, beam carrying fractional topological charges that may not survive for a longer distance. This is what is reported, but we have not checked with that.
Okay, thank you.
Is there any question? No.
Yes.
This quantum-based cryptography and this optics-based cryptography.
Yeah, in optics-based cryptography, we deal with the optical properties of the light. Like optical properties means you can vary the amplitude, you can vary the phase, you can vary the state of polarization, you can vary the spatial frequency, you can vary the wavelength, you can vary the orbital angular momentum. This topological charge you can vary. I am encoding a light beam with a topological charge 1 and maybe 1.5. For decoding, we have to use minus 1.5. So these are the different degrees of freedom what optics provides. In quantum field, you have only spin half what you all deal with them. But I am not a quantum expert, so I cannot comment on that.
But because normally quantum cryptography applied in the communications.
Yes.
Where I think it is based on optics only. I think angular momentum, whatever you are talking
Everything
about.
it is all
because it's all quantized again.
Yeah, it is quantized again. So basically, you have to have the light beam. And we play with I do not claim in the quantum area, but I claim to be a classical optics person.
Yeah, again, in algorithmic side for detection, there is something called diffusion algorithms.
Yes.
Which is being used heavily because it's similar like large language models.
Yes.
Basically, it actually encompasses every aspect of the scientific or non-scientific, everything whatever possible is available on the images. It is being captured in this one. Same way large language model, because language contains all knowledge, whether it is scientific knowledge or mathematics knowledge, it's all contained. Same way, diffusion algorithms work similar.
So that is purely digital.
It is
Your
actually diffusion algorithms.
It is purely digital. In the digital encryption, they use it.
Yeah, yeah. So that could be also very much useful.
But we don't use that in optical cryptography.
Okay.
Optical cryptography, we purely use the properties of the light, and we control the properties of the light and create these crypto systems.
Okay. Thank you, sir.
Okay, thank you again.
Thank you.
Thank you, Professor.
As a token of appreciation, we would like to present a memento to our esteemed speaker. I request the chair to present a memento. I request Aparna to bring the memento, please. As a token of gratitude, we would also like to present a memento to our session chair, Dr. Satpathy. I request Professor Sandeep Dhara, Director, Material Science Group, IGCAR Kalvakam, to present a memento to our session chair. I request Priya to bring the memento. Thank you all. This ends today's technical session. Now I request all of you to proceed for tea. There is a cultural program at 18:30, just after 45 minutes probably. So all are requested to assemble and attend the program. Thank you.
की धारा देकर, उच्च विचार की धारा।
चार नंबर माइक किसके पास है? है लगा है। आपको 6 माइक लगेंगे एक एक्ट में, तो उसको भी टेस्ट कर लो एक बार।
हेलो, हाँ शर्मा जी ये माइक है।
ठीक है, इको चाहिए इसमें। गाना गाओगे क्या करोगे? ठीक है, ये म्यूजिक के हिसाब। एक बार चुपके से ले रहे हैं, एक बार चुपके से ले रहे हैं, एक बार चुपके से ले रहे हैं, एक बार चुपके से ले रहे हैं।
Hello, 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 hello. हेलो इसको बढ़ाना हाँ लेते हेलो 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 गरज गरज आज मेघ घनन घनन छायो रे दमक दमक चमके भेजुरी कहता ऋतुराज आयो री
हेलो ऑडिबल क्लियर इतने में ओके हेलो अ वेरी प्लीजेंट इवनिंग ग्रेट नृत्य जब बोलता है तो शब्द मौन हो जाते हैं. Let us now witness the harmony of music and the discipline of dance all together. चलिए चलते हैं भारतीय संस्कृति के संगीत और नृत्य के एक ऐसे सफर में जहां हर ताल, हर मुद्रा और हर भाव हमारे शास्त्रीय संगीत के परंपरा की विरासत है. Let's welcome upon the stage the next performance, the classical evening, the classical melody that is now going to rock the stage. I guess there's going to be some time. Till then, I have something with me. मुझे शेरो शायरी का बहुत शौक है और मिर्जा गालिब का एक शेर मुझे याद आता है. आप सभी की तवज्जो चाहूंगा कि दिले नादा तुझे हुआ क्या है, दिले नादा तुझे हुआ क्या है, आखिर इस दर्द की दवा क्या है. हम हैं मुश्ताक और वो बेआजार, या इलाही ये मसरा क्या है. मैं भी मुंह में जबान रखता हूँ, मैं भी मुंह में जबान रखता हूँ, काश पूछो कि मुद्दा क्या है. जबकि तुझ बिन नहीं कोई मौजूद, तवज्जो चाहूंगा कि जब तुझ बिन कोई नहीं मौजूद, फिर ये हंगामा खुदा क्या है, ये हंगामा खुदा क्या है. Let's welcome them upon the stage. Let's begin the first classical program of this event with a huge round of applause. Come on. अक्सर ये सोचता हूँ, क्लासिकल जो नोट्स होते हैं उनमें मदहोश करने की ताकत होती है। जब आलाप लिए जाते हैं तो उनमें गुम हो जाने की ताकत और आरज़ू होनी चाहिए। जब आप इस संगीत का मजा लेंगे तब आप सभी से रिक्वेस्ट है, फील, बिकॉज दिस इज जस्ट नॉट द परफॉर्मेंस बट द एक्सपीरियंस इंडीड। आप सभी की थोड़ी सी तवज्जो चाहूंगा। इरशाद, तहजीब रफ़ी की एक बहुत अच्छी गज़ल है। इस गज़ल का नोट जब तक हमारे परफॉर्मेंस रेडी हो रहे हैं कि सुनिएगा। तेरा चुप रहना मेरे ज़हन में क्या बैठ गया, इतनी आवाज़ें दी कि मेरा गला बैठ गया। तेरा चुप रहना मेरे ज़हन में क्या बैठ गया, इतनी आवाज़ें दी कि मेरा गला बैठ गया। यूं ही नहीं कि फ़कत मैं ही उसे चाहता हूँ, जो भी उस पेड़ की छाँव में गया सो बैठ गया। यूं ही नहीं कि मैं ही फ़कत उसे चाहता हूँ, जो भी उस पेड़ की छाँव में गया वो बैठ गया। इतना मीठा था वो गुस्से भरा लहजा मत, इतना मीठा था वो गुस्से भरा लहजा मत पूछ, उसने जिसको जाने को कहा वो बैठ गया। इतना मीठा था वो गुस्से भरा लहजा मत पूछ, उसने जिसको जाने को कहा वो बैठ गया। और उसकी मर्जी वो जिसे पास बैठा ले, उसकी मर्जी
रचना जो मैं आपको सुनाने जा रही हूँ वो राग दरबारी पे आधारित है। যে তোমার, শুধু যে তোমার, আমি যে তোমার। मेरे ढोलना सुन, मेरे प्यार की धुन, मेरे ढोलना सुन। मेरी चाहते तो फिजा में बहेगी, जिंदा रहेगी होके फना। तननन तुम तननन तुम तननन तुम तननन तुम, तान देर देर ना। मेरे ढोलना सुन, मेरे प्यार की धुन, मेरे ढोलना। सांसों में तेरी सरगमी है, अब रात दिन। जिंदगी मेरी तो कुछ ना अब तेरे बिन। सांसों में तेरी सरगमी है, अब रात दिन। जिंदगी मेरी तो कुछ ना। मेरी धड़कनों की सरगोशी तेरी धड़कनों में बजती है, मेरे ख्याल में हर पल तेरे ख्याल शामिल है।
मुश्किल बड़े ही मुश्किल है। धनी नि धनी नि धनी पद 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 गम पद नि
As a part of this last medley, which is based in Rag Yaman, we have selected a few songs which are evergreen songs. और जिन लोगों ने इन गानों को गाया है उनकी एक विशेषता रही कि उनकी आवाज़ ही उनकी पहचान है. So that is why the name of this medley, which we are about to sing, is called मेरी आवाज़ ही पहचान है. It's a kind of tribute to all the legendary singers of our country who gave us such amazing songs. And for this medley, we would like every one of you to join, because all of these are evergreen songs and I'm sure we have heard them in some point in our life. So let us sing this medley together. चेहरा ये बदल जाएगा, मेरी आवाज़ पहचान है, गर याद रहे नाम गुम जाएगा, चेहरा ये बदल जाएगा, मेरी आवाज़ ही पहचान है, गर याद रहे. I want everyone to join in the next song. चाहे बना दो, चाहे मिटा दो, चाहे बना दो, चाहे मिटा दो, मर भी गए तो देंगे दुआ, मर भी गए तो देंगे दुआ. आंसू आवाज़ें बहते हैं तो बहने दो मुझे, तुमसे मोहब्बत हो गई है मुझे, पलकों की छाँव रहने दो, एहसानों के Let's hear it from you. Let's try one more time. Thank you so much for joining in. You all have a wonderful voice.
What a blissful performance. Indeed, मेरी आवाज़ ही मेरी पहचान है. गरज गरज का संगीत हो या मेरे ढोलना के सुर, वाकई में. It was really pleasant and beautiful. Thank you so much. Let's give them a huge round of applause. As I said, classical performances are not just performances. They are the experience. And I hope you had a great experience listening to such melodies. Let's change and tweak the test for a while. Let's have an event with vibrant energy. After all, lots of students and lots of energy is here. And so, to feel such energy, let's welcome a surprise element dance upon the stage with a huge round of applause.
రాజమండ్రి రాగమంజరి మాయమ్మ పేరు తలవనోళ్ళు లేరు మేస్తిరి కళాకారుల ఫ్యామిలీ మరి నే గజ్జ కడితే నిద్రపోదు నిండు రాత్రి
సోకులాడి స్వప్న సుందరి నీ మడత చూపు మా పటేల మల్లె పందిరి రచ్చరాజు గుండె ఊపిని నీ పంక చూస్తే గుండెలోన డిరి డిరి డిరి
కుర్చీ
ராஜாவுக்கு எல்லாரும் சொல்ல இவனை தொழுவானா என்னும் ஜனத்திலக்க காலம் எடுத்து வச்சால் சொர்க்கம் போலும் எல்லும் மினாக்கி அண்ணன் தனி நாடு போல மல்லும் மினாக்கி எல்லும் மினாக்கி அண்ணன் தனி நாடு போல மல்லும் மினாக்கி
అతిరవ్వ మాదిరి ఉంటాడే నా సావే మెత్తాని పత్తి పువ్వుల మరి సంటాడే నా సావే
உண்மையிலேயே வர சொன்னாங்களா?
சார் என்ன சார் இப்படி கேட்குறீங்க? சத்தியமா வர சொல்லிட்டாங்க சார். அண்ணா அடி அடி.
Such a power-packed performance, right? Once again, let us show the energy back. I am really thankful to the Culture Club who has organized such a blissful event and cultural evening for tonight. Here's certain glimpse, and I feel very proud to let you all know that from the last year, Culture Club has started to giving it back to the society. And giving back to the society means dance, music, and everything culturally to old age homes. Here are certain glimpses from last 3 or 4 events that we have done so far. I would request you to please show the glimpse.
जिंदगी सफर टुकड़ों में जैसे कहानी है बटी शाम है काली सी कोई स्याही लिख दो इससे तुम्हारी कहानी तुम हो मुसाफिर और जिंदगी सफर टुकड़ों में जैसे कहानी है बटी लंबे लंबे रास्तों पे जिंदगी है छोटी सी इस पल को जी लो जैसे पल है कोई आखिरी बीते लम्हों को बुला के पल थोड़े से चुरा के बीते लम्हों को बुला के पल थोड़े से चुरा के पल धीरे धीरे बहता जाए जाए पल धीरे धीरे बहता जाए जाए
तुम किससे कहे और आवाज पहुंच रही है
फासले दो कदम की दूरी लगे मेरे लो खड़ी फासले जिंदगी कभी भी कभी खुद की नजरों से लफ्ज़ बरसों से
एक और शेर आज की शाम के नाम इस बार इजराज प्लीज बिछड़कर उसका दिल लग भी गया तो क्या लगेगा बिछड़कर उसका दिल लग भी गया तो क्या लगेगा वो थक जाएगा और मेरे गले से आ लगेगा ये बिछड़कर उसका दिल लग भी गया तो क्या लगेगा वो थक जाएगा और मेरे गले से आ लगेगा मैं मुश्किल में हूँ तुम्हारे काम आऊँ या ना आऊँ मुझे आवाज़ देना तुम्हें अच्छा लगेगा मैं मुश्किल में हूँ तुम्हारे काम आऊँ या ना आऊँ मुझे बस आवाज़ देना तुम्हें अच्छा लगेगा मैं जिस कोशिश से उसको भूल जाने में लगा हूँ मैं जिस कोशिश से उसे भूल जाने में लगा हूँ ज़्यादा भी अगर लगा तो एक हफ्ता लगेगा मैं जिस कोशिश से उसे भूल जाने में लगा हूँ ज़्यादा भी लगा तो एक हफ्ता लगेगा मेरे हाथों से लगकर फूल मिट्टी हो रहे हैं मेरे हाथों से लगकर फूल मिट्टी हो रहे हैं मेरी आंखों से दरिया देखना सहरा लगेगा अभी हाल ही में मैंने एक शेर लिखा था मेरे हक में नहीं कि कोई मुझे खुशियाँ अदा करे ये शेर मैंने खुद नहीं लिखा था मेरे हक में नहीं कि कोई मुझे खुशियाँ अदा करे मुझे तो चाहिए कि खुदा मुझे मौत अदा करे मेरे हक में नहीं कि कोई मुझे खुशियाँ अदा करे मुझे तो चाहिए कि खुदा मुझे मौत अदा करे और मैं उसके हर लहजे पर मरता हूँ मैं उसके हर लहजे पर मरता हूँ उसे तो चाहिए कि ज़माना भला करे उसे तो चाहिए कि ज़माना भला करे मैं अक्सर सोचता हूँ कि कभी कभी ऐसे इंसान खुलता है तो पानी की तरह खुलता है धीरे धीरे फैलने लग जाता है मुझे समेटने में फिर एक अरसा लगेगा खैर वक्त बीत जाता है यादें रह जाती हैं एंड टुडे वी आर क्रिएटिंग सच अ मेस्मराइजिंग मेमोरीज एक मेरा शहर पतझड़ से वीरान है, एक तेरे शहर से सावन नहीं जाता। एक मेरा शहर पतझड़ से वीरान है, एक तेरे शहर से सावन नहीं जाता। सोचता हूँ मुझे तेरी आंखें नजर आती है, कश्मकश ये है कि तेरा चेहरा नजर नहीं आता। और तुझे तुझे जमाने के दुख, दर्द, आंसू सब नजर आते हैं। तुझे जमाने के दुख, दर्द, आंसू सब समझ आते हैं। सवाल ये है क्या मेरी आंखों का दरिया नजर नहीं आता? बहुत बड़ी गजल है उसकी, कुछ 3 मसले सुनाए थे। ओके, ग्रेट, लेट्स वेलकम देम। अमेजिंग इवेंट, another amazing melody, सुरों का ताल का संगम। कहते हैं कि समय ठहरता नहीं है, बट उसकी धुनें हमारे दिलों में हमेशा राज करती है। जैसे गुलजार साहब ने समय को लेकर कुछ कहा था कि वक्त रहता नहीं है टिककर, आदत उसकी भी इंसान जैसी है। गहराई की बात है, पर माना कि सच है, समय किसी के लिए नहीं रुकता, पर हम अपने दिलों में इन लम्हों को सहज कर रख सकते हैं। आज की शाम को सहज के रख सकते हैं, तो जब कभी शाम ढले और सुरों की धुन गुंजे, तो यादों की किताब में उम्मीद है कि आज की शाम गुलजार रहे। फिर मिलेंगे एक नई शाम और नई यादों के साथ में। Once again, thank you so much to be here around us. The last thing is to appreciate everyone who has put up so much of efforts to be here, to give this energy onto the stage and to set all of our heart on fire. I request Dr. C.P. Paul sir to please come up on the stage. I request Dr. S. Majumdar sir to please come up on the stage and share the mementos to Group 1. I request Pratishtha Jha, Prachi Malakar, Ananya Agarwal, Kavita Jagtap, Manika Verma. I request Dr. C.P. Paul sir to please present mementos. Paul, sorry, S. Majumdar sir, so sorry. Thank you so much. I request you to please be seated. Next, I request Dr. Ajit Upadhyay sir to please felicitate Group 2. I request Sakshi Dubey, Shivansh Dubey, Avni Yadav, Pranjali Soni, and Garima Ramteke. Avni Yadav, Pranjali Soni, and Garima Ramteke. Thank you so much, sir. Please be seated. Next, I request Dr. N.S. Banerjee, sir, to please facilitate Group 3. I request Dr. S. Satpathy, sir, to please facilitate Group 3. And I request Arjun Pachori, Moksh Jain, Avni, Siddharth Jain, Rishabh Gupta to please come up on the stage. Thank you, sir. I request you to please be seated. I request Dr. Ramakant, sir, to please come up on the stage and facilitate Group 4. On students, I request Apara, Aditya Dusane, Pooja Shekhar, Khushi Sharma, and Russell Brown to please come up on the stage. Thank you, sir. I request you to please be seated. Next, I request Dr. Vijay Dwivedi, sir, to please come up on the stage to facilitate Group 5. On students, I request Utkarsh, Sarthak Sangamnerkar, Sneha Garg, Sanskar Saxena, Pratyush Kulkarni to please be on the stage. I request you to please be seated, sir. I request Dr. S. Majumdar, sir, to please come up on the stage and facilitate Group 6. I request Aditya Samarth. Next, I request Akshat Shah. Next, I request Amitesh Sharma. I request Bhupen sir to please come up on the stage. Also request R.K. Yadav, sir. The last memento of the evening to the first person who did and who acted as a convener for this cultural evening, Dr. Preeti Jain. Please, huge round of applause. Yeah, sure, sir.
It was when she proposed that this cultural evening will be conducted by Cultural Club of Medicaps University, and she showed certain glimpse of their performances, past performances. So we were thinking that it could be probably most fit for, for the annual function or something like that, So, and since this endless crowd is a mixed crowd and it's a different crowd, so we were a little bit, concerned about what actually would turn up. But today, what we experienced is really, really, that is far beyond our expectation. And let me tell you, the person behind this is Dr. Preeti Jain, who happens to be the organizing secretary, but she is a chemist. And you must know that she did her MSc in chemistry, inorganic chemistry, then did her PhD, and then again did her MSc in organic chemistry. So it's a mixture of organic and inorganic. So that fusion we have seen here. So you know that organic and inorganic, this fusion is very much evident in her creative performance by her team. So it's a big applause for her and her team.
थैंक यू सो मच सर. सर उस समय तो ऐसा लगा था कि आपको थोड़ा भरोसा नहीं था, बट दैट टाइम आई टोल्ड यू कि सर थोड़ा सा भरोसा रखिए, बस उस समय तक आप बस जब 8 की इवनिंग होगी उसके बाद फिर हम लोग बात करेंगे. एंड थैंक यू सो मच सर. आरआर के जो भरोसा हम लोगों पे दिखाया है कि हम लोग शायद प्राइवेट यूनिवर्सिटी थे तो सर को स्टार्टिंग से थोड़ा सा कम भरोसा था, बट अब शायद सर अब लगता है सर शायद आपको बहुत ज़्यादा भरोसा हो गया, और हो सकता है सर नेक्स्ट टाइम भी आप जो है एनालिस्ट के लिए मेडिकेप्स यूनिवर्सिटी को ही चूज करें. थैंक यू सो मच.
So it was a great evening. I hope you had a great time. And जब भी किसी गुलजार शाम को याद करोगे तो शायद मेरा चेहरा नज़र आएगा, शायद मेडिकेप्स की ये शाम नज़र आएगी. Thank you so much. You all can proceed for the dinner.